Hi. Well, welcome everyone to this joint NASA ESA session. My name is Jonathan Bamber. I'm president of European Geosciences Union as of about 10 minutes ago. But actually, I'm also an Earth observation scientist that has done a lot of work with both NASA and ESA missions over many years. And we've got a really fantastic session, and we're kind of European, North American double act here. So my co-chair is Steve Graham from NASA, Goddard. And without further ado, we will kick off with the first invited presentation, which is going to be given by Mike Frelich, looking down on the Earth, how satellites have revolutionized our understanding of our home planet. And he might say a few words about, I don't know, NASA Earth Science Program in general, possibly. Let's see.
Let's see.
We'll give you 25 minutes, and then, is
perfect.
Yeah. Okay. Brilliant.
Okay. Well, thanks very much, and thanks to all of you for taking time out of your busy science day to hear some programmatic and science overview talks. And it's my great pleasure to be presenting to you a snapshot of where we are in the NASA Earth Observation Program. And I won't talk too much about science today because that's what you all do. But in the past, we've talked about how satellites revolutionize our view of the Earth from the vantage point of space. And today, what we're going to be focusing on is how, as a mature field, we are using our observing system in new and relatively revolutionary ways. Next, please. This is possible within NASA because NASA itself is a full service, if you will, program in Earth science. We not only fly missions, but we also have a viable research program to answer the key question of what is the Earth? How do we understand the Earth as an integrated system? Not simply individual processes, but the linkages between processes. We have a strong applied sciences program to take the measurements that we get from the flight program and the understanding from the research program and turn that into efficient, focused information products for users, as I like to say, for non-satellite weenies, those who may not be technically oriented, but who need the information in order to make decisions. And underlying it all, of course, is a strong technology development program where we are maturing the technologies, both hardware and software today, so that they can be incorporated into the missions of tomorrow. Next, please. And so on one chart, this is our flight program, both present and future for the next several years. And you can look at it approximately this way. All of the missions from about here on down, from Cygnus on down, involve on-orbit missions that are flying today. Missions or large instruments, focused instruments. And there's approximately, depending on how you want to count, between 17 and 19 of those. Many of them multi-instrument spacecraft, some of them focused spacecraft, and we'll talk quite a bit about them. But on orbit right now, we have 17 to 19 missions or large instruments making many different measurements of many different variables of the Earth system. And that's, of course, key. Being able to make measurements globally, but with high resolution over long periods of time, but with frequent sampling at any place, allows us, and from many different variables, allows us to not only look at individual processes, but multiple processes and the connections between them that define our environment. On the upper portion of the chart are our future missions. The dates down here are the dates of the on-orbit missions, how long we expect them to be lasting, at least, and the dates for the yet-to-be-launched missions are the dates for their launch or for instrument delivery. And there's approximately the same number of planned missions to launch between now and 2023 as there are on orbit right now for the NASA research fleet. Next, please. Now, we've heard that the new administration has made a budget proposal which will make the NASA Earth Science Division program somewhat smaller. They have identified 4 missions for potential termination. I won't spend the rest of my time going over the US budget process, which is fascinating in the extreme. But it's a long process, and the President's proposal may or may not come to pass. But 4 missions, 1 on orbit, the Earth observing instruments on the Discover spacecraft, and 3 for development, OCO3, Clario Pathfinder, and PACE, an ocean color instrument, an ocean color mission, a carbon measurement mission from the space station, and a climate trends mission have been identified for potential termination, but the rest of the program that is up there remains. And if you go back and forth, Steve, between the previous one and this one relatively quickly, you can see that although the program is going to be getting smaller, it is not an existential cut to the Earth Science program in NASA. That's what I want to get across to you, and I'm happy to answer questions afterwards. Next, please. And coming up at the end of this year, much awaited, we will have the second Earth Science and Applications Decadal Survey from the US National Academies of Science, which will advise NASA, US Geological Survey, and NOAA, along with the administration, about the science community's and the applications community's views on where the Earth Science programs of our nation should be going in the coming decade. So this is all background, if you will. Next, please. Let's look at how we are using the observing system that we have today. And we are making revolutionary as well as evolutionary steps away from the old way of doing business, which was individual missions with individual science teams answering focused individual problems, if you will, to a way of doing business in which we can state a science problem or a large applications need and combine through free and open data exchange between missions and between missions in NASA, between US missions, and internationally, we can combine all of the measurements that are needed in order to address the science. And what I'm going to do here in the rest of the talk is basically show some examples of how it is that we combine measurements from multiple missions. We all know about the International A-Train, 6 or so missions which are flying in close physical proximity, physical formation, making measurements of many, many, many different quantities. We call it a heterogeneous constellation, and making those measurements nearly simultaneously. We can do that. Now we can fly missions 100 kilometers apart in space, or 17 seconds apart in terms of when they're crossing over a particular point on the Earth. So we can make virtual observatories that are far larger and than could possibly be done with any single mission where we hang a lot of instruments on them. We also have homogeneous and semi-heterogeneous constellations as well. Next, please. The Global Precipitation Measurement Core Observatory, joint between NASA and our Japanese colleagues, JAXA, along with a large number of other missions, are for the first time providing near global rapid measurements of precipitation over the entire globe, with resolutions in space of 10 kilometers or so and temporal resolutions of 30 minutes or so. Prior to this, we knew that it rained, especially when I went on vacation. We knew that it rained where I was going to be, but there were not good measurements globally with more or less uniform accuracy of precipitation. We could not close the hydrologic cycle sufficiently well. By combining measurements from many different instruments on different spacecraft, we can now get accurate, global, high-resolution in space and time measurements of precipitation over the Earth. Next, please. Another semi-homogeneous constellation, if you will, is provided by Landsat and Sentinel-2 from two different organizations. Sentinel-2, of course, being the ESA and European Commission terrestrial measurement mission that Joseph is going to be talking about a lot, and Landsat being the US multispectral set of missions that extends back nearly 45 years now. Our longest time series of moderate resolution, 30-meter or so, multispectral, consistently processed land measurements over the globe from space. For the first time, by combining measurements from both Sentinel and Landsat, we can get very high temporal sampling over particular sites. And shown here is a particular county in Wyoming where, as time went on last year, there was irrigation, there was precipitation, there was also cutting of alfalfa fields for the grass, for the hay. Either one of these measurement systems alone would not have the appropriate temporal resolution to be able to resolve the near instantaneous events here. However, by combining the two sets of measurements, intercalibrated, consistently processed, we can actually get information on the vegetation types and their changes over this period of time that's better than anything that we could have gotten individually. Next, please. Turning now to purely homogeneous constellations, we are combining measurements from identical spacecraft flying in formation specifically to gain high temporal resolution information, mostly about atmospheric effects in areas such as the tropics, where severe storms and other phenomena evolve rapidly. Next, please. In the future, using one of the recently selected NASA Earth Venture instrument proposals that was recently selected, called Tropics, Time-Resolved Observations of Precipitation Structure and Storm Intensity, with a constellation of 3U CubeSats, we will be flying 12 or so CubeSats in formation over the tropics from about plus or minus 30 degrees or so, each one of them making vertical soundings of precipitation, temperature, and humidity. So multiple satellites, all of them intercalibrated, all of them identical, flying very rapidly over any particular point, can be combined, the data can be combined to get a high temporal resolution view of rapidly evolving systems. Next, please. Today, in the tropics, we are making measurements of surface winds and air-sea interactions from the Cygnus constellation of 8 small satellites. These are a little bit bigger than the 3U CubeSats of tropics, but nonetheless, it's an 8-satellite constellation using reflected GPS from the sea surface in order to measure wind speeds and air-sea interactions in the rapidly developing eye walls of tropical storms and hurricanes. Because the GPS and the other GNSS measurements are at L-band, this for the first time allows us to penetrate the heavy precipitation regions in the, that are present in developing tropical storms or in evolving tropical storms and hurricanes. For the first time, getting high temporal frequency measurements that will unlock, hopefully, the secrets and the mechanisms that cause tropical disturbances to evolve. With the 8 Cygnus satellites orbiting between about plus or minus 25 degrees latitude or so, we are getting measurements over every point about every 2 hours. Combining the measurements from the multiple satellites then gives us an unprecedented view of the evolution of particular storms. Next, please. And this mission just launched when did Cygnus launch? It launched in December. December 15th, I think, as a matter of fact. Well, I was supposed to be at AGU. Ah, yes, it's all coming back. It launched in December. They've learned how to fly the satellites. We not only have first light, as shown here, demonstrating that, in fact, the reflected GPS signal can, in fact, be autonomously measured from each of the satellites. Each one of them, by the way, looks at 4 reflections simultaneously from 4 different GPS. Next, please. But also, we can relate those measurements to wind speeds as estimated, for instance, by ECMWF or other model predictions. And what we see here is a particular tropical storm, Inawo, over near Madagascar. One of the Cygnus satellites passed over the storm. As you can see here, it passed over a little bit of Madagascar as well, measuring the reflected GPS signal from the sea surface, and you expect the bistatic cross-section to go down as the wind speed goes up, and you see extremely close correlation between the prediction of that particular storm and the measurements from this Cygnus satellite. So we have the ability to launch multiple spacecraft, all of them identical, to space them out in orbit, and thereby to make high frequency, high time resolution measurements. Next, please. We are using the space station as a platform, the International Space Station, as a platform for Earth observations. Is it precisely the right platform that we would want? Probably not. On the other hand, the nations of the ISS partners have spent well over $100 billion of money to make that infrastructure. We get very low-cost launches and low-cost operation. All we have to do is build bare instruments and mount them on the space station. So if we can get 80% of the science that we might want to get out of an instrument for 30 or 40% of the cost, not counting launch vehicles, and a free launch as well. It is a useful science platform. Next, please. And you can see that we are using the space station fairly extensively. At the moment, there are 3 instruments which are operating on the space station right now: Earth-observing NASA instruments, the Cloud Aerosol Transport System LiDAR instrument, which has been up since 2015, the recently launched Lightning Imaging Sensor, which was launched in mid-February, along with the SAGE-3 atmospheric profiler and trace gas measurement instrument. These 2 were launched together on a space station resupply. Now, I don't know about you, but some of the things that I find that some of the things they do on the space station are really cool. One of them is how they took these 2 instruments, and SAGE-3 in particular, from the launch vehicle that went up to the space station, which also had important space station supplies, socks, underwear, food, oxygen, some rodents apparently, and mounted SAGE-3 on its location here at ELC4. Next, please. This is an animation, but it is actually highly high fidelity animation. They went in with the arm to the Dragon capsule. They took SAGE-3 in 2 pieces off. They put SAGE-3 on the Metro. They detached the arm and moved the Metro over to another point on the space station, reattached the arm, and put the instrument on its nadir viewing platform. That's the nadir viewing platform, and then they stuck the instrument on it. Okay? This all happened over a period of just a couple of days, and it is absolutely amazing. And this is not the first time that we have done that. You saw that RapidScat flew on the space station for quite some time. That also was installed robotically, as was CATS. So we are using the space station to do science. It's there. It's in an orbit that, for instance, for SAGE-3, which does occultation measurements for limb sounding, it's almost a perfect orbit for that. And we are sufficiently mature as an organization and as a science that we don't have to focus simply on what we design, but rather we can use the available investments that others are making in order to revolutionize our view of our planet. Next, please. And finally, we are starting to use excess capacity on commercial communication satellites in geostationary orbit. In our NASA program, next please, we recently selected the GeoCarb mission to make carbon dioxide and carbon dioxide, carbon monoxide, methane, and solar-induced fluorescence measurements from geostationary orbit. Next, please. This is a little bit about the instrument. It is not, it's the same measurement approach that is presently flying in the Orbiting Carbon Observatory 2 in low Earth orbit. By placing an instrument like this in geostationary orbit, we can make measurements rapidly over an area similar in size to the Amazon or the continental US or other similar areas as you'll see in a bit. So we can make very frequent measurements and thereby avoid some of the issues associated with clouds and other phenomena which complicate the retrieval of carbon dioxide and SIF measurements from OCO2, for instance. And one can conceive, of course, of this kind of measurement system where, similar to the meteorological satellites, where we have multiple ones in different areas from different countries, making global coverage to allow us for the first time to really get a handle on the fluxes and the processes which cause carbon fluxes between the atmosphere and the land and the atmosphere and the ocean. Next, please. And this just shows that GeoCarb will in fact be launched in about 4 years or so on a geostationary communications satellite. Next, please. And before that, in the 2019 or at most 2020 timeframe, we will similarly be launching an instrument called TEMPO to make measurements of ozone, nitrogen dioxide, and formaldehyde, air quality measurements, again, from a commercial geostationary satellite. TEMPO will be able to make frequent measurements over virtually the entire area of North America, and more importantly, next, Steve, TEMPO, coupled with a sister instrument which is nearly identical, GEMS, being launched by our Korean partners, and in collaboration and complementary to Sentinel-4, we can have almost global major land area coverage with frequent measurements from geostationary orbit. This is the revolution that you are living right now, where we don't simply have to make measurements and analyze them from individual spacecraft, but can rather put together measurements from many different spacecraft, many different missions, many different quantities to understand our Earth as a system. And so I'll leave this on for the question period. Again, this is our NASA research fleet, both on orbit down here and planned here, along with a variety of other instruments. So thank you very much for your time.
Okay, thanks very much for that fantastic talk, Mike. I think if there's any of the audience who are not satellite-based scientists out there, they must be thinking of a career change after listening to that, because it was amazing, some really amazing science. We do have time for questions. Yeah. Oh, yeah.
I can hardly see here. So.
He's going to the mic. So,
okay.
Yeah.
Yeah, I'm Stef Lermit from Delft University of Technology. I first want to thank you for these amazing data sets. I think it's wonderful what you at NASA do. I had a question about the data availability on big data platforms. Is there any prospects from NASA to provide this multi-source, multi-satellite data on one platform?
So we have our Earth Science Data and Information System is a heterogeneous data system that attempts to look homogeneous from the outside. We make all of our Earth observation data freely and openly available with no period of exclusivity or anything like that. And you can get at the EOS DIS or the ES DIS, the Data and Information System, through any of a variety of portals. You don't need to know where the data are in order to get into the system, and you don't need to know where the data were coming from in order to order it and download it.
But my question is more, is there any prospect to have it on a big data platform where you don't need to download the data, but you can process the data at NASA's or whatever big data facilitator facility?
That's also an excellent point, and we are trying to move to do some pilot work in that direction. Okay, there are tensions, of course, between the availability of the resources on the big data side and the need for certain levels of security on the government side. However, we are trying to push against the IT people, let me just tell you that. In the agency, we're trying to push a variety of different pilots along those lines. I believe that in 5 or 6 years, we will probably be there.
Okay, great, thanks.
Yeah. Do you want to use the mic just behind you? Do you want to get...
Greg Kopp from the University of Colorado, and this year from the Max Planck Institute as well. Wanted to ask, with the new decadal survey coming up, if you take these as opportunities to evaluate, kind of give yourself a report card on how have we done in the last one, what have we achieved, and what are we going to be doing differently, evaluating the recommendations from the next one. How does NASA perceive any changes that you might be doing with the next one coming up based on how the last one has gone for you?
Good question. Very, very briefly, it was on the slide and I didn't really go over it. The first decadal survey that came out was very specific in terms of missions. Right. This decadal, if they follow the statement of work, which is always a crapshoot with the national academies, we asked them this time to identify science priorities and to present reference missions, but not specific missions. Then it will be our intent over about a year after the decadal survey comes out to do the system engineering to take those science priorities and translate them into a collection of missions. Meanwhile, this decadal, we've also asked them to look at the legacy recommendations from the first decadal, rank them as well. So some of them may have been overtaken by scientific advances. Some of them may remain relatively high priority. Some of them that were lower priority before might be increased in priority. And so we've asked them for that information as well. Their recommendations, coupled with the plans of our partners and leavened by fiscal reality, budget reality, will define our program over the next decade or 15 years.
Yeah, great. Thank you, Michael.
And by the way, I realized that I forgot to say one important thing about SAGE 3. SAGE 3 was not only a NASA instrument, but the precision pointing platform for SAGE 3 that actually allows it to follow those occultation events was a contribution by the European Space Agency. Otherwise, Joseph would come up here and I wouldn't have a ticket home.
We can take one more quick question. Yeah.
Manuel Grande from Aberystwyth University. I'm more a member of the upward-looking than the downward-looking community generally. I was extremely impressed with your constellations of cross-calibrated satellites, and I recall that always used to be hard, and in an era where we're moving more and more into CubeSats and so on, it's somewhere where you can really see that we're moving. And I wondered, A, if you had advice, and B, what you thought would come next in that way.
Well, let me give kudos to ESA and NASA. One of the reasons that we could put Sentinel-2 data sets rapidly together with Landsat data sets was that while Landsat 8 and Sentinel-2A and 2B were being developed, tested, and calibrated, we actually exchanged calibration sources so that on the ground, to the extent possible, each one of those spacecraft and instruments was cross-calibrated against the other's calibration source. We're thinking ahead. We recognize how important that is. And we have strong enough collaborations with partners and like-thinking partners like ESA, like other European space agencies, like JAXA, et cetera, to be able, we think, to be addressing these issues from pre-launch to post-launch. We fly aircraft flights designed to underfly Cryosat-2, for instance, to provide correlative measurements. And it happens in the other direction as well.
Okay, thanks very much, Mike. We better press on. Mike's here for the rest of the day, and there will be time for questions, which I'll say something about in a minute. But we're very fortunate, as well as having Mike here, we've also got the head of ESA in here, Josef Aschbacher, and he is going to give us a talk on ESA Earth observation missions at the service of geoscience.
So thank you. Thank you very much for the for this introduction. Can you hear it? Yes? Is the microphone on?
Okay.
Yeah. I would be just too glad to keep Mike in Europe to hold on to his ticket and not let him travel overseas back anymore and stay with us, because he's so inspiring, and it's really a pleasure every time to see and to listen to his presentation. What I will do is show you the activities of the European Space Agency. Some of it is quite complementary to what we do with NASA. We do it, of course, with our member states who are funding our activities. Some of them together as a hardware together with our member states, some of them within the ESA context, but of course we are quite closely and very, very nicely working together with the partners, of course, within Europe, with NASA, and with other partners worldwide. The next slide, I think I have to, yes. Shows a similar graph as the one you have seen before, but for the ESA missions. So what you see here is, again, 3 types of orbits, or 3 circles. They are the missions, they're not divided into flying ones and future flying ones, but more into different categories. You see on the outer circle the meteorology missions, the ones that we are actually developing and have been developing for EUMETSAT, or together with EUMETSAT, since a long period of time. Some of you may know that EUMETSAT is actually taken out of ESA as an entity. It used to be a department within ESA and then became an international intergovernmental organization. So since the 90s roughly, but the first meteorological missions were built within ESA, and now they are done by ESA but for EUMETSAT. So this goes back to the actually 70s. In 77, the first Meteosat was launched, a geostationary meteorological satellite. And then ever since we have been building by now 8 geostationary satellites and also polar orbiting satellites with EUMETSAT. The cooperation, I have to say, is really a very, very good one, in the sense that EUMETSAT is taking care of the user requirements, is defining what parameters need to be measured, and us, as ESA, we develop the satellites for EUMETSAT, who then operates these satellites and provides the data to the meteorological community. The next circle is on Copernicus. So this is really our newest child, but a very successful one and a very intense one in terms of missions which we are building and developing. This one is done together with the European Union, who is formally leading Copernicus as a program, which also has a services component and an in situ component. And we as ESA, we are leading the space component, meaning again the definition, the development, the operation of the satellites, and the provision of data to the users. This is a system that is being built up. I will show a few more slides, but this is something that where we started the first mission, the first launch of the first mission in 2014, but now we are successively building up this chain of observation types over the next couple of years. And then you see the inner circle, which is the green one, which is science missions, which is actually really addressing questions of science raised by top scientists around the world. But of course we have bodies which are defining what do we need to measure in order to really advance some important science questions. Just to name an example of a more recent selection, the scientists have asked us, in order to better monitor agricultural production, food security, you would need a sensor that measures in the fluorescence part of the spectrum, and therefore really measures something that is not yet visible with your eyes or in the near-infrared spectrum as you used to be, but really measuring fluorescence activity, and therefore a mission was defined to do exactly that. There are a number of those missions that have been developed and have been launched. We have now 8 of these Earth Explorers in orbit. The 9th one is currently selected, and there are future ones to come of this type. I should also say that these green missions, as you see them in the color here, are very challenging, also from a technology point of view, sometimes so challenging that we get to a blocking situation where the mission, the system engineers, the space engineers suddenly get stuck with certain development, and we really have to overcome some technical hurdles in order to continue and to complete the mission development. An example of this is ADM Aeolus, which will be launched later this year, which has a laser on board on the UV part of the spectrum, something that has never been flying before, not even by NASA, which usually is doing a lot of very fascinating cutting-edge technologies. And we got stuck along the development, and it really cost us a lot of headache, a lot of work to sort out the technical issues in order to complete the instrument development. And now, thank God, and knocking on wood, we have gone through the valley, and we hope to launch this mission by the end of this year. But this really shows also that we are going into domains where, of course, a commercial company would not go because they wouldn't take the risk. But also this is typically work for a government research organization like ESA to explore these type of technologies. So let me go into a bit of details into these various missions. Copernicus is the first one. So what is Copernicus? It is, as said before, an integrated system of observing the planet with different parameters, with different instruments, in order to get a holistic view of the various elements of the Earth system. And this is at a scale of environmental observation, so not for security, just to be very clear, where the resolutions, for example, of the sensors are in the order of 10 meters, 20 meters or above, so which is really looking at the key parameters of our planet Earth, of the atmosphere, of the surface, of the oceans, of the polar caps, and so on. It also is really addressing some of the questions which have been raised from a scientific point of view, but which have become more mature and are addressed in a more operational manner through an operational constellation. This shows some of the Sentinel series which are being prepared to fly or which are already flying. As you see, we have 6 families of Sentinels in orbit or planned to be flying in orbit at the moment. We are, together with the European Commission, discussing further evolution of this system towards Sentinel 7, 8, 9, possibly even 10, to have other parameters added which are complementing the measurements we are doing today. Just very briefly, Sentinel-1 is really a radar mission which is continuing measurements of Envisat and ERS from the past, and is providing, with 2 satellites, these C-band measurements on a routine basis. Sentinel-2, as it was mentioned by Mike, is quite comparable with Landsat. It's not exactly the same mission, has some differences in terms of characteristics, but is also a land mapping, land monitoring mission to have routine products for land mapping and therefore agricultural applications, forestry applications, coastal applications, to really provide this data for a number of disciplines. Sentinel-3 similarly has a suite of instruments, both in the optical domain but also an altimeter for wave height measurements for climate change parameters, but also other ocean measurements, in combination with optical instruments at a higher, larger scale of resolution from in the near infrared, in the visible range, but also in the thermal infrared, to have a more global but more frequent observations of various parameters. Then Sentinel-4, we have heard before, on geostationary orbit, measuring atmospheric chemistry, together with Sentinel-5 and 5 precursor, measuring various parameters which are, of course, essential to better understand climate change and the changes of our Earth system. And Sentinel-6 for altimetry measurements, again for climate and ocean measurements as they come. Let me just point out the last point, the last bullet of this slide, which is the free and open data policy, which is something we have been fighting for quite intensely and quite hard in Europe to get this adopted. It is not a given that we can give away this data for free to everyone. I'm very proud and very happy that this is taking place, and for the EGU community, I think this is a very important achievement, because you can really use this data, download them from the internet, and use them for your purposes, which I think is very, very important, very essential to advance science, but also knowledge of the Earth system at large. So the next one shows the Sentinels. As I've mentioned them before, with some of the launch dates. Today we have launched 5 of these Sentinels. The last one was Sentinel-2B, and the other ones, as you see here, they will be launched in the next coming months and years in order to build up this constellation. This is the first image of Sentinel-2B, which is taken over Brindisi. Brindisi, some of you might know, is an Italian word and also means cheers. So it was really a cheers of Sentinel-2B in order to show that it works very well, and the data can confirm of extremely good quality and really very well complementing those of Sentinel-2A, which is already in orbit as a sister satellite of 2B. Let me just flip through a few examples to highlight some of the applications or the uses of this data. The first one you see here is interferometry, a discipline which is actually very well used by today, and I have to give credit to Fabio Rocca, who is speaking right after me, for discovering it and really making good use and broad use of this technology, which really allows from 800 kilometers in space to detect changes in height of concrete elements on the ground in the order of millimeters accuracy. And this is quite an achievement. I still remember when this new technology was introduced in the early 90s, the room was packed because everyone was so excited to see what comes out from this new method, which really Fabio was, together with his colleagues, was discovering and really showing how it works. So what you see here is different colors, meaning different changes of the surface height, in the order of millimeters to centimeters. The upper one is Envisat, which was taking, in this case, the measurements from 2002 to 2010. The satellite itself lived up to 2012. But you see here some changes in the blue domain, which is areas that have been sinking, which have been, increasing, and the red ones which have been decreasing. So you see here the order of magnitude is centimeters per year. If you compare this then with Sentinel-1A, which is the more recent radar satellite, using the same technology but with more frequent observation, first of all you see that it's more dense, but also you see that some of the deformation, at least on the scale here, a bit larger. What you see here is the changes around the Vesuvio area. There can be Flegrei, but it will be up to Fabio to really explain this in much more detail because he is the expert on this domain. But the same technology can also be used, as you see here, for ice sheet velocity change measurements. Again, very useful information for many of the applications. Similar example, this is the earthquake of Italy, which we had last year. It is 120 kilometers north of Rome. Actually, I remember it. It was shaking quite a bit also down in Rome. What you see here with the same technology are the areas that have been increasing in height and decreasing as a result of the earthquake. These are two images taken from Sentinel-1A and 1B. And you see the blue area here, which was actually increasing in height, about more than 30 centimeters here. And the red area is the one that has been decreasing in an equivalent manner. So really quite a shift of terrain here as a consequence of the earthquake. Similar example here, a more recent example of Mocoa in Colombia, which had a major landslide, if you remember, with quite a number of casualties, where you see the same technology applied for seeing the changes of height. Again, areas which have been decreasing in height and others which have been increasing. So this really has caused or is becoming a major application on a more routine basis. What you see here is the Antarctic Larsen C ice shelf. You probably remember the Larsen A and the Larsen B ice shelves have been cracking off some already 20 years and 15 years ago. And now Larsen C is really having a major crack, which we see developed here. You see it on this line, which is shown in this interferogram, which shows very clearly that there is ice being, there's a crack and the ice will break off, and this will cause or will create the largest iceberg which we have ever measured, because this part here, this portion north of this part close to the sea will break off eventually and really create a huge iceberg, which of course has major impacts on several fronts. Let me talk about the access to this data. What you see here is some statistics of data access of Sentinel data. We have today on the open data portal about 75,000 users registered, downloads of about 25 petabytes of data. The data hub availability is 98% over the last month. and the products which have been published is published in the sense of put online is in the order of more than 2 million. Another graph that shows this quite impressively also is how this data uptake is materializing, which is shown in this green curve here, where you see Sentinel data mission users from the Open Data Hub, which is going towards the 70,000. This is a different date compared to the one before, but it's above 70,000. And it really shows how steep the usage of this data is taken up by the user community by registering on the online website and downloading this data. What you see also in comparison is more the classical access to data of ERS, NVSAT, but several of the Earth Science, Earth Explorer missions, which is much slower and much more steady because the community is much more focused and has a much more smaller reach of people. But with the Sentinels, we really enter into a big operational supply of data for many users, way beyond the scientific community, really into operational communities, but also commercial communities. And this is becoming really an important step for us as ESA, because suddenly we're in the midst of big data, and the user community gets a very different one, a very demanding one, in order to cope with this. A few more examples to show some of the Earth Explorer results, and I'm flipping through those a bit faster. The SWARM mission, which is quite an exciting mission composed of 3 satellites orbiting in tandem and measuring magnetic strength. What we see here is the jet stream which was measured in the Earth's inner core, of the iron core, which was discovered based on these measurements of the SWARM satellites. In fact, we had quite a large SWARM and cryosat meeting in Banff a few weeks ago, where some of these results were presented. Another example here, a combination of SWARM with CHAMP measurements from DLR, which shows the magnetic field of the lithosphere. And you see here in these colors the variations of the magnetic field, which is quite impressive and quite amazing, with red having the higher values of nanoteslas and the blue ones towards the lower ones. But the variations on the globe of this magnetic field strength is actually quite fascinating. Another example is the digital elevation model of Antarctica, derived from Sentinel-1 images, or Sentinel-1 measurements. A first of its kind with this accuracy, especially, of course, over the Antarctic, where you have constant cloud coverage, and therefore the use of these radar images and radar data is quite important. Let me show another example, just flipped one, of some of the measurements we're doing with ESMOS, soil moisture and ocean salinity. It's a satellite which is actually not designed for ice thickness, but we have discovered that for thin ice, these measurements are extremely good and extremely useful and quite complementary to those of cryosat, which is designed to measure ice volume and ice extent. So the combination of these two measurements is shown here, where you have in this moment here a combination of this graph here flips between ESMOS measurements, ESMOS and cryosat measurements alone. So you really see the combination of these different data sources gives you a more complete picture of both thin ice and thicker ice, and a more frequent observation and a more coherent coverage of area. Again, here an example to show the measurements taken by various satellites on ice thickness, ice volume. Here we have worked very well together with NASA, and I should give credit to the work of NASA and its scientists, which were supported through the NASA network, in working on a project or a program called IMBI, which has compared all the relevant measurements of ice, both of European, of American, and other data sources, and really established the truth of what is the rate of melting, or the rate of increase or decrease of the mass balance. And this, of course, has been a major exercise. Several tens of scientists have been working on it for quite a few years in order to analyze all this data. And one of the results of this exercise is that you see here the changes of ice volume in square kilometers per year during this period, as compared to later on with cryosat. over Greenland, and you also see quite a drastic increase of the change of or the reduction of ice volume over these periods. The next slide shows the result of some of these melting or reduction of the ice volume, which leads to an increased sea level rise. We are going back here to measurements of the early 90s, 92, with some of the first altimeters, which are over time complemented by different other altimeters. You see in the various colors here, the various satellites that have been measuring sea level height, but they all show the same signal that we have a constant increase of sea level height over the years, on average in the order of 3 millimeters per year. And if you extrapolate this into the future, into 50 years or 100 years, you can imagine what this means for our ocean level, sea level, and to some of the areas which are at sea level, which of course will be highly endangered or possibly some of them disappearing because of the sea level rise, which is a fact. This brings me to one of the last slides, which is climate change. We're also funding within ESA a big initiative called Climate Change Initiative, where we look at various parameters. You see some of them listed here, where we take all the satellite data which are available or accessible to measure these parameters and really define and determine, as I've shown before for sea level rise, the various parameters and see how they change over time in order to better understand our climate system and our Earth system as a whole. And I can just invite you to look at the website. There is recently there has been an app released to look at various of these parameters. It's very nice and very flashy, but it really gives you very valid information on some of these parameters which are listed here on how they change over time. And last, just to invite you to visit our booth. We have a major booth downstairs on the basement, on the ground floor, which is quite nice. We have a large team of ESA people waiting for you there, showing you various things which we have. Also, we have demonstrations of software tools of various aspects, which are running all day long and throughout the whole week. And please visit us there. Some of the colleagues are sitting in the room here who will then answer questions or give answers to some of the issues like accessing some of the data, Sentinel data access, and similar things. And last, very last, to say that tonight there's also a town hall talk here in-house in room L2 from 7 to 8 in the evening, and I would very cordially and very warmly invite you to join. It is more an open discussion, so there will be a short presentation, but it really is the place to look a bit into the future and see what are the challenges that are coming up, not only for ESA, but in Earth observation in general, how we can respond to these, and I really would hope to have a very interactive dialogue and discussion at this event. Thank you.
Thanks very much for that. I can vouch for the booth. It's great, and it's right next to the NASA booth, so you can do two at the same time. Questions for Joseph? We have time for questions? Yeah, do you want to use the mic? It's just behind. Because there's a lot of people sort of coming and going.
And I'm Christina Astrodu from ESA. I just wondering why the cryostat data is only for 2011-2012.
Sorry, which one?
The cryosat.
Cryosat was launched in 2010, exactly, voilà. 2010, so this was the first 2 years where the data were taken. Of course, the measurements are ongoing. You could do the same thing up to today. So these measurements exist. It's just a matter of having, when the exercise was done, it was done for 2 years. But the cryosat works perfectly fine, actually so fine that the scientists are coming to us and want an extension of its lifetime, which is good news. It's bringing very good data on a routine basis.
Because the reason I ask is that would be interested to see more years in order to compare, because it seems like quite a large gap between the changes shown previously and those shown with the cryosat. So maybe like a few more years to see like if those are like really the
No, absolutely. We have to combine the various data. I mean, cryosat is one satellite, brings fantastic data, but we have to combine it with all the other ICE missions, both existing today but also measurements that have been made in the past to overlap and cross-calibrate the various satellites. And there we really work extremely well with NASA and other partners to do this exercise. And I think this is probably one of the domains, apart from the Landsat and Sentinel-2 domain, where we work very well in cross-calibrating and using both agencies' ICE measurements to have time series which are continuous and give you a continuous information. Yes, a very good point. Mike is mentioning there's an IMB2 exercise. I showed some of the examples of the IMB1 exercise. And this is now being repeated because it is found so successful to really cross-calibrate the various measurements and see what is the actual state, so that we decided to launch an IMB2 follow-on of this project to again do this in the future to have similar series as done for IMB1 also for the future. And this is one of the major activities where we work together extremely well.
Okay. I had a quick question. Actually, yeah. Do you want to?
Yamauchi from Kiruna. How often do you define the new Earth observation mission? Like a SWAM, it was decided about 10 years ago, but then when do you decide a new type of the science mission? And is it the ESA who decides, or is it the EU who decides the new mission?
If I understood you correctly, is how often you define new missions?
Yes.
Yeah, okay. No, this happens regularly. It depends on these three strands which you have seen in one of the first slides. Yeah. If it is a metrology mission, it is done on, I would say, regular basis together with EUMETSAT. And there we develop typically batches of satellites, say 4 satellites, and then we launch them one after the other in order to have a long time series and really make sure that we have about 15 years of coherent data sets of one type of information. And this is done together with EUMETSAT in periodic steps. If it is the Sentinels, which you have seen before, we do this together with the European Union, European Commission. The partnership is in a way that ESA is funding the development of the first satellite, and the European Commission would fund the recurrent satellites and their operation and their launch. So, but this, of course, goes hand in hand. For example, for Sentinels 1, 2, and 3, we have 4 satellites each. And these 4 satellites, we develop the first one. We build all 4 together to save cost. And then we launch them, so in this case, 2 pairs, so 2 plus 2, one after the other, in order to really have a continuous series. And then afterwards, of course, we replace it by a new generation, which will be, again, defined with new parameters and new user requirements. And on the science missions, there we have periodic calls to scientists to come with science questions to be answered or to be addressed by Earth observation missions. And this is happening on an irregular basis, but on average every 2 to 3 years, where we have such a science call. And this really is driven by budget availability in order to fit, I would say, the budget envelope with the money we can spend on these missions.
Thank you.
Thank you.
Okay, we better move on. We're just running a little bit behind time, but that shouldn't be a problem for reasons I'll explain in a minute. But next up, Fabio has already had a little bit of an introduction from Mike, I think. Fabio Rocca is going to talk about ubiquitous and continuous SAR imaging for natural hazards, present and future of remote sensing. And this is one of the kind of more science-focused, if you like, of the presentations in this session. So, no, sorry, wrong one. Yeah.
Thank you. Thank you. First, we would like to thank Dr. Aschbacher for his very kind words. Indeed, it has been for me a very great pleasure to be able to work together with ESA in the last 30 years. However, now I'm going to talk about possible futures. I don't have the crystal ball, but indeed what everybody would like to have is a continuous and ubiquitous radar observation of the Earth under the clouds day and night. Is this possible? How we can do it? Will we ever see it? So this is next. How to go to the next?
I think it should. I can do it.
This one? Oh. This one. Thank you. Okay, so the first question is, geosynchronous observation system, is it a pie in the sky? Is it something we will never get? Let's ask, okay, we want 3-meter resolution, X-band, because it's reasonable, higher frequency is worse, lower frequency is worse. It would be 150 kilometers wide antenna, and because we are away 36,000 kilometers. It's a big thing. However, we can obtain it with a single satellite librating every 12 hours. So the idea is, if we accept a reduced time resolution, just 12 hours, and so we look at only at the things that are stable for 12 hours, then a single satellite could do it. And then we could have ubiquitous, continuous, 8 hours. We want to get better. So if the antenna is spatially sampled, say 200 times, we need 200 satellites? No, we don't. But anyway, so then we would need 3.5 minutes to fill. So if we want to have an ID, a new image every 3-4 minutes, we would need 200 samples of this antenna. But this can be obtained with just 20 satellites, not 200. And a rather small satellite, 3-meter antenna, 500 watts. So the pie in the sky is basically obtained with 20 satellites and not nano satellite, but mini satellites. However, if we want to go even faster in time, we want to go from 3.5 minutes to, say, 30 seconds, then we need 60 satellites. So we go with the square, or the square root, if you like. So this means basically that it's not impossible to have, say, 3 minutes observation time, ubiquitous, all time. We need 20 satellites. And now the point is, how do we get that? Okay, these satellites librate in the sky in the geosynchronous orbit. They watch the Earth any place. The antenna diameter is 3 meters, 50 watts each. In 7 seconds, we get a new image, not perfect, that will increase up to 20 minutes, and then in 20 minutes, we get a nice image. Actually, with 20 minutes would be for 6 satellites. For 20 satellites, as I said, it would be 3 minutes. So this is a long-term goal, but how to get there with a reasonable sequence of experiments? This is what we hope we can get, but how we can get there? And so this is the outline of my short talk. First, we discussed the geosynchronous star concepts, then how a communication satellite compatible system would work, and then the applications, and then the challenges, and then a 6 satellites constellation could be a second step towards the goal. Okay, so what we can get with a single satellite librating in the sky, going back and forth 150 kilometers in 8 hours. Well, every 15 minutes, we could get a very coarse azimuth resolution, 500 meters, 15 minutes, but using interferometry, this means that we can find the average distance from the ground every 15 minutes, and this means that we can get every 15 minutes the water vapor on land with a resolution of 500 meters. If you heard the first talk, we're talking about 10 kilometers resolution, about 20 minutes or so. So really, with a single satellite, we could get a good result using, again, interferometry and libration. Every 2 hours, we are spanning a wider antenna, we increase the resolution. Every 8 hours, we get full resolution. What kind of satellite would be? Well, this was the satellite we are studying now. Would be a compact satellite that could be carried out by the Vega. Vega is a small launcher of the European Space Agency. First in LEO, in low Earth orbit, and then could transfer to GEO in 160 days with electrical propulsion. This is the trajectory from LEO to GEO. Compact SAR, hybrid antenna, immediate data download. So it's not a big thing. It's not a big satellite. It would be a satellite, 1,000 kilograms satellite, and could do the job. What kind of job? Well, for one, it could just watch this area of the ground and could point its lobe here, say, or here, or here, or here, or here, electronically. And so basically, one could revisit within this area everything in, say, minutes or actually seconds. So one could move the main lobe from one place to the other. Then, mechanically, one could, now in minutes, one could point the whole set from here to here to here to here, because everything would be visible in from the satellite, and so one could focus his attention on any of these locations. So we see that actually, I was saying ubiquitous is not exactly ubiquitous, because all this could be, say, 12 hours dedicated to this area, 12 hours dedicated to that area, but obviously everything would be completely flexible, and so in real time one could move the area of interest, where after that one would have the ubiquitous possibility. So this is really for hazards. So basically, once you know that there is a hazard, you can point the antenna over there, and from this moment on, you have the continuous visibility I'm talking about. And so if we look at the desired coverage in days per year, depending on the location, we see that for X-band we need for agriculture 200 days, L-band 305 days, so for only 35 issues for flooding, or 30 for volcanoes. So we see that all these conditions could be accommodated by a single satellite that could work over the continental area and could act as a continuous observation for all these things. And this is a single satellite. So you see what this satellite would do. It goes back and forth, this synthetic aperture. In 1 hour, it describes this. And so this is the antenna that is being covered by just one satellite. And so just to cover the full aperture, it takes 8 hours. But in any time, in any hour, okay, at the end of the, it would spend less time at the end. But anyway, to cover the antenna. What happens with two? So now we start getting hungry. So instead of one satellite, we say we have two. And with two, actually, we gain something, because we have also the intermediate solution with the third. So this illuminates, this receives. It's like having one here. So with two satellites, we have 3 phase centers, and they go on with a square. And so basically, it would be in a much better situation. And so the full coverage would be obtained in much faster time. So in 60 minutes, one would obtain 40% of the coverage, so already, say, 15 meters resolution, but in 60 minutes. So you see that with two satellites, you are getting a much faster response, and obviously you are spending twice as much. Okay, we'll move. What kind of application? Well, this is the first interesting application. This is a big landslide in an open pit mine in the United States. And actually, using radar, it was possible to save all lives, because it was possible to tell people to move before this landslide was happening. So this is the situation where this kind of satellite would be used. So actually, we could measure atmospheric water vapor, soil moisture, earth, and then for solid earth earthquake, volcano, landslide, subsidence, flooding. For cryosphere also would be interesting, because we could measure snow cover, snow mass, glacier motion, and obviously for soil moisture, agricultural monitoring, hydrological monitoring. So for all these applications, even a single satellite would be useful. And then would use the motion, the correlation with the interferometry, and the backscatter amplitude. All these magnitude would be measured to make the result. And then we move to the actually I see 5, but to the 6th satellite, to a constellation. In that case, we would have a full constellation of 6 satellites, and you see that we have many more than 6 satellites, because all these red points are with this satellite transmitting and the other transmitting, so the midpoint is useful. And you see that as you see, most of the time, the whole area, the whole antenna is being populated, so basically we have a really continuous view. With 6 satellites, we could get the idea of a continuous monitoring. They would fit 3 and 3 on a single Ariane launch, and indeed it could be, now this is not the first experiment I should advocate, but certainly after a good result with the first satellite, it could be joined by more and more satellites to get this result, this final result. So you see that it's a pie in the sky, yes, but not so big. So maybe it's accessible. These are the already existing solutions for mini-SAR that typically this one has been proposed. This is a CubeSat with a 1 meter antenna available today and with low Earth orbit, certainly not for the high Earth orbit. But anyway, this means that even for the technological level that we need, as I was showing you, we are not so far from reaching that. Okay, so this concept combines three concepts, different: geostationary orbit, synthetic aperture radar, MIMO, because actually each radar is transmitting and receiving at the same time. So we gain a factor n square in the signal-to-noise ratio because we have n times transmitters, n times antennas, so we gain a factor n square. We gain a factor n times n plus 1 over 2 in revisit because we have this is the number of phase centers. Is scalable, is robust. One satellite dies out, we have the other. Is reconfigurable anytime we can. So it's the advantage of the geostationary orbit is because there is continuous visibility, there is safer from the debris, and obviously the advantage of the synthetic aperture radar is that we have day and night observation and sensitivity to millimeter deformation and all the other possibilities. So my conclusion is that, okay, these are all the possible results that can be obtained, real-time flood forecasts, soil moisture, storm modeling, landslides, all sorts of possibilities. And ship motion, you would be able to see snow cover, snow mass, and depending on the kind of users, civil defense, farmers, meteorologists, they would say, obviously this is a result for the big thing, that is 6 satellites. With 1 satellite, you have all these things, but not every 10 minutes or 20 minutes, but every 8 hours. So the limitation of the concept. Do we have limitation? Yes, we do. First is the fixed view angle, because we are incidence to latitude. High latitude are not very visible. Indeed, even in Norway, you have a satellite antenna that look practically over the horizon. These could be some targets, but certainly I would say that this is good for the very northern latitude. The other problem is long time image cause fast target to vanish. Water is just black because in the time we are measuring it, it changes the distance from the satellite, changes the phase, and it's gone. So really, fast targets are not visible. And there is no resolution for 25% of the time. We have a single satellite. And finally, the continuous spectral occupation. This is probably the worst problem. In other words, if we are saving signal-to-noise ratio, it's because we are transmitting all the time. This means that we are using the band all the time. So really, we do need a general agreement on if we want that kind of system, say, to dedicate part of the available bandwidth. That's why I'm talking about X-band, because we have enough band at that frequency, so that we can devote a part of the band for continuous spectral occupation. Otherwise, indeed, we have to migrate to even higher frequencies. It's doable, but more complicated. We don't have the technological level at the moment. So the number 2, 3, and 4 are mitigated in the multi-satellite configuration. So my conclusion are that geostationary orbit brings a visit time from weekly to hourly, opens new opportunities that only a day and night weather microwave sensor can fully exploit. And Geostare, the single satellite, and then Argos, the 6 satellite new observation, may enable monitoring of fast evolving water vapor, soil moisture, flooding, soft dam, landslides, glaciers, snow cover, infrastructure stability, and coherent changes. Geostare will be proposed again as in the next venture is Earth Explorer number 10. And I'm done. Thank you.
Okay, thanks for that, Fabio. So we have time for one quick question. Has he convinced the guys at ESA or not? Does someone at the back? Yeah. Okay.
Hello, this is Nino Mei from University of Bremen. I have a question actually regarding to this one and as well as the two talks before. So I think this spaceborne platform definitely provides a very powerful tools for getting data, and this kind of consolidated concepts trying to unify different data, but anyhow, the final output will still have this temporal continuity and special consistency problem. You anyhow composite your data from different observation time and different regions, and is NASA or ESA has any plan to actually observe the Earth from different platforms, like for example?
I'm not sure, what's your question?
The question is that because you anyhow combine different data from different time observation and different region, so the final output will anyhow not consistent for a single time point.
Did you get that, Fabio? Yeah, we're running out of time.
I agree. Obviously, you don't have, with this system, with the big system, the 6 satellites, since it's 3 minutes to have an image, you can point it electronically everywhere. So basically, you can get not only the continuity, but also the ubiquitousness. With the single satellite, you don't get basically the ubiquitousness at the level of a single hour. You get it at the level of a couple of days or 3 days. So more or less the same thing as with Sentinel-1, only that you do it with just 1 satellite. But then you can focus on a single area. In other words, if you have an hazard and you want there the continuity, then you point it on that area. From this moment on, you have the time continuity. Did I answer your question?
Okay, we need to press on. Thanks a lot for that, Fabio. Really, it's sort of provocative idea, certainly. So the last talk in this session, which focuses on Earth observation, is going to be given by Marcus Rothacker, and it's geodetic Earth observation. And again, this is more of a kind of science-focused presentation.
Yes, thanks for the invitation. Ladies and gentlemen, good afternoon, everybody. In this 15 minutes, I would like to give you some ideas of what geodetic Earth observation means and what contributions we can give to Earth observation in general. I will start with a short motivation, show slow and fast processes that are important in the Earth system, a range of different scales. I will then talk about 2 different contributions, one coming from the space geodetic techniques, namely especially GNSS, VLBI, laser ranging, and DORIS, and I will concentrate here mainly on GNSS, considering the solid Earth, and then go to the gravity missions that have made a big progress in static as well as time variable gravity, and then say a word about the global geodetic observing system, something about the future, and come to some conclusions. The motivation. When we look at the Earth systems, then it is really covering different processes lasting for millions of years, like plate tectonics on this side, or decades, like the melting of ice sheets, but also effects that are in seconds, in minutes, like earthquakes, tsunamis, or volcanoes. So for this, we see that we have challenges. The challenges are, among others, reliable detection of small signals over long terms. That means we need long time series from reprocessing of ground and satellite data. On the other hand, we have the very fast processes where we need real-time processing. We need early warning systems for tsunamis, earthquakes, and so on. Not to forget what was already mentioned is the integration of sensors, the combination of sensors is vital nowadays. It's the only means to separate the signals with complementary data. And finally, seeing the huge amount of data present nowadays, we need methods of visualization, we need information and knowledge management to deal with this amount of data. Now let me start first with solid Earth, plate tectonics on the one side, the slow processes, and earthquakes as the fast processes. I concentrate here on GNSS. No? We see here a reprocessed time series from GNSS data, just one station of 260 that we were processing over many years. It is a station to see the detection of small trends. It's a station Alberta in Canada. The first you see is north, east, and up components, and you see the accuracy of the daily solutions that are about 2 to 3 millimeters every day. This allows us to really look into many details. For instance, over here we seem to have some sort of a jump here. Geophysical interpretation is asked. No, it is just an antenna change. So we have to be very careful with our interpretation of results. The antenna was changed on the GNSS pillar. I do not want to show this. The actual thing I would like to show is this. In the east component, you see that after about 14 months, the situation is changing with the coordinates over 1 to 2 weeks by about 8 or 6 millimeters. This is called a silent earthquake, taking place over 2 weeks. It's also called episodic tremor and slip. This is something we could not have seen before having GNSS available, GPS available, because these seismometers cannot really integrate. Let me go on to the global picture. Here you see that nowadays the Earth is covered with permanent GNSS stations. They show you all the continental motions all around the world, and this network is growing as we are staying here and listening. We see all the major movements. We can identify where the critical zones are. This is one of the big achievements that we can get with GNSS. Let's now go to the fast events. You see here a unique country that has made a plastering of all its landscape with GNSS receivers. There are many, there are about 2,000 such receivers, and I would like to show you the Tohoku earthquakes that we analyzed. The horizontal motion on the left side, the vertical motion on the right-hand side, and if I get the cursor here, we start, you see the epicenter. Sorry, just a moment. So you see how the Earth is deformed, close to the epicenter, and then you see all the waves propagating through all Japan. This is 1 second data of many hundred stations that you can see here, and finally you have the displacement over all the globe. You also see the height component over here. Also in the height, you see nicely how these waves are propagating. And in future, we can imagine that such a picture can be given in real time. All these stations are connected in real time, and it is just a question of a few more years to be there. Let me show that GNSS is not only allowing for positioning. It also allows to detect delays in the signals by the atmosphere. We know this atmospheric water vapor, or the electrons, the free electrons in the ionosphere. Here on this side we have the Swiss Alps, and we can see the tomography that was done with GNSS stations on both sides, north and south of the Alps. Sorry. Go back. So. And you now see how the tomography of many stations can give you the distribution of water vapor in the atmosphere and shows the gradients there are above the Alps. Here, on the other hand, we have the electron content, where we can see the density of free electrons around the globe as it is changing with the position of the sun. So all this can be done by ground networks, and we already saw there are more applications like reflectometry and so on. One additional thing I would like to mention, monitoring of snow with GNSS. You bury a GPS receiver in the ground and let it be covered by snow. The snow will cause a delay, and this delay can be captured, and you see here in blue you see GPS, in red you see a balance where the weight of the snow was measured. And you see that they agree very nicely over this few days of winter. And so you can get the water equivalent, not the snow height, the water equivalent, which is very important for hydrologists to know about what will happen in spring. Let me now switch to the gravity field. The gravity missions, static and dynamic. We have two major missions that are important in this context. One is GOES by ESA. It has finished its life 2013. It's mainly there to get a high-resolution static gravity field. The main instrument in there is a gradiometer that allows to measure the distance, the differences of the gravity acceleration around these three axes. And with this, you can get very interesting information about the gravity fields. The other mission is GRACE, cooperation of NASA and Geoforschungszentrum DLR in Germany. It's mainly there to do the temporal variations with a resolution of about 10 to 30 days. The main instrument is the K-band, link with an accuracy of about 5 micrometers. And with this, we can now see, first of all, the static part by GOES. The main information is a geoid. Here, we subtracted all the low wavelengths parts so that you see the details. And you see all the details that are important for geophysicists. You see all the subduction zones. You see all those areas, mid-Atlantic ridge, where geophysical processes are happening. When we take this geoid and we add altimetry, combination of different satellite missions, altimetry delivering mean sea surface topography, then we can subtract the two, and what we get is the surface current speeds. I will not show the full movie, but maybe start somewhere, somewhere here. And you see all these nice details of the currents propagating in the oceans. You see, for instance, here the Gulf Stream. You see here the meandering of the Antarctic circumpolar current. And you see here in this area, if the time is correct, also effects like El Niño. Let me go to the short-term processes, or shorter-term processes. This is Greenland ice sheet loss. We already saw it before, over 10 years. And what we see here is that the ice is melting away. Even it seems that it is accelerating. We also see the annual fluctuations very nicely. And this is the mass. This is not the volume, which is very important to think about, because the mass will go into the ocean and not the volume. Let me go to one more such picture, also provided by JPL. This is the Californian drought. And I think when we zoom in into California and look over several years what happened there, then we see that GRACE mission can really see into the continent. It can see how much water there is because it's measuring the mass. And every mass that is moved will be seen by GRACE. So you see that the situation is not yet as difficult, but when we now go towards 2014, 2015, then we really have an extreme dry area where all the water has gone in this continental part of the US. So GRACE is able to capture all these phenomena. Let me now give an idea of what the Global Geodetic Observing System is. It is supposed to be the umbrella of all this. So, on the one side, we have the observations, the space geodetic techniques, VLBI, SLR, and so on, satellite missions, and we also supply this with, or complement it with terrestrial data, and from this we can get the geometry of the Earth, station positions, sea level rise, deformation. We can get Earth rotation. I didn't talk about this here. Would also be fascinating. And the gravity field and its temporal variations. These are called the 3 pillars of geodesy. And from this, as we have seen, we get information about the atmosphere, the oceans, hydrosphere, cryosphere. And this is interesting because when we know more about this, we can better interpret our 3 pillars, and we can think about innovative techniques. Satellite missions that will fill some gaps in this system. Not to forget, we have to combine all this. We have to make use of all these sensors together. And on this side, we need the interactions. We need to know how these different components interact, and not just look at one individual component and model one individual thing. And for geodesy, primary goal of highest importance is a reference frame. Highest accuracy and long-term stable. The biggest error in sea level nowadays is the reference frame. Not the amount of glacier melting, not the amount of ice sheet. It's the reference frame. Thinking of a system that guarantees over 10 years 1 millimeter correct coordinates everywhere. It's almost impossible. And that's why we have to work on this. So let's go to the future very briefly.
briefly?
The space geodetic techniques will get bigger and bigger in the sense of satellites. GPS is complemented by GLONASS, Galileo, Beidou. 120 satellites will be available in a few years. The networks are growing. Japan, Europe, the US, and so on, even Switzerland, I should mention here, have permanent networks. There will be more than 10,000 stations very soon. In the satellite area, we have more and more constellations and formation flying, and also the other techniques have new telescopes and technologies now available. When you look at the satellites, then for us, the most important mission is certainly the GRACE follow-on, planned to be launched in 2018. It is a cooperation of NASA with the Geoforschungszentrum in Potsdam. And the important thing is to continue this time series and to fill the gap before we have a next generation gravity mission. What is also interesting that this mission will have a laser ranging interferometer flying with it that proposes to get a factor of 100 in accuracy compared to the old GRACE mission. This is certainly of highest interest to NASA as well as ESA. Here, showing that GRACE flow is coming, temperature and vacuum tests, one of the satellites here. And finally, I would like to talk very briefly about eGRASP, a derivation, so to say, of GRASP that was proposed to NASA. eGRASP Eratosthenes is a new geodetic reference frame mission. It is a proposal for the Earth Explorer Call 9. And the interesting thing is that it really makes exactly the combination we were talking about so far. On board there will be also systems, GNS, SLR, VLBI, DORIS, and so on. And we aim at determining the inter-system biases that are most important for the reference frame on the 0.1 millimeter level. There will be a high precision clock that will connect all these systems from the time basis, and it will also be connected to the ground with T2, L2 terminals. There will be a very high accuracy accelerometer, and the orbit is very interesting. It will be highly eccentric. That means we will, I'm through in a moment, we will be able not only to look at the unification of the reference frames, but also at geocenter and scale, altimetry and sea level, but also relativistic physics from this very eccentric orbit. This brings me to the conclusions. Geodesy can contribute significantly to the monitoring of our restless planet. GEGOS, the Global Geodetic Observing System, is a geodetic contribution to Earth observation, and it is a meteorological basis for all Earth observations, establishing and maintaining the global reference frame. Thank you for your attention.
Okay, so I will make my announcement now, actually. It may appear that we've run over a little bit. We have run over a little bit. But actually, the talk immediately after the coffee break has been cancelled. And that was a 30-minute invited talk. Unfortunately, the person giving it missed their flight. So we've actually got about 50 minutes for the coffee break if you're staying in this session, which is why we've been a little bit more relaxed about the timing. So before you all disappear, Marcus will be around if you want to ask him questions. But I'd like to thank all the speakers for a really fascinating session this afternoon. So if you could give them all a round of applause, please.
No, it's better like that. Okay. So welcome to the second part of the session on Union Symposium ESA NASA. So as you know, there's been few changes in the program. Unfortunately, Imtiaz Ali Khan couldn't come, so there was one talk cancelled. The next talk will be about NASA's Heliospheric System Observatory. It was supposed to begin by Stephen Clark. Unfortunately, he was not able to come. The talk will be given by Mona Cassel. So please.
So do I have control of this, or do I ask you? Can you hear me? That's not...
Here by the mouse. Just click it and go.
Okay. Good afternoon. Clearly, I'm not Steve Clark. I found out, I guess, Friday that I was going to give this presentation for him, so please forgive me if I look at notes occasionally. I got the slides on Saturday before I left to come here. Okay, so let me go through just the outline of what I'm going to cover. We'll do some program highlights, talk about sounding rockets, future mission opportunities, interdisciplinary science, international partnerships, and communication and outreach. Hopefully I'll have enough time to cover all of these topics. So, program highlights. Okay, starting with the System Observatory. I like to wander when I'm on stage. Is there a way I can take something? I don't like to stand still, or I could speak loudly.
Pointer here.
Does it? Okay. All right, thank you. Careful. Okay, so our System Observatory. So you can see over here in the, let's see, that's the pointer, the Voyager's 2 satellites. Clearly they are not here in relation to everything else. We are not exactly sure where they are. I mean, some people think that they have crossed out into the interstellar medium. I think that is still a point of discussion. I don't think we have a final answer for that yet, but we have had these Voyager satellites for 40 years. Coming up, I think in September this year, there is going to be a big celebration at the National Air and Space Museum in Washington, D.C., and I think we have got William Shatner, Captain Kirk, to come and give a cameo. So that'll be pretty exciting. So those are the oldest 2 satellites in our armada. Whoops. Let's see, back. Okay. But we have some others that are fairly old also. We have the ISTP era satellites, Geotel, which is a JAXA mission, but had some NASA components on it. SOHO, which is an ESA mission, and also had some NASA instruments. And then also WIND, which actually ought to be up here, but it actually did cross into the magnetosphere during its lifetime. So those are our oldest ones, but we also are showing up here some that are still in development. We have ICON, which I'm going to talk about, give a whole slide on, GOLD, Solar Probe Plus, Solar Orbiter, and then the SET mission. Now, the SET mission has actually been ready and sitting on a shelf for a couple of years. I think it's an Air Force launch, and it is ready to go. So hopefully it is a space environment test bed. So hopefully it will launch within the next year or so, so that it's not old technology by the time it launches. But I think there's a good chance that it will actually launch in the next couple of years. And then we have, of course, all of the other in-between satellites. It's quite a large group of satellites, and we continue to support them for as long as they're operational. Okay, here is a different view of the same group of satellites. I will show, well, I do show now everything is green, everything is operational and working quite well. MMS is the only mission still in its prime phase. It launched in 2013. 15. So its prime phase is ending in September. We do have one problem with stereo in that we lost contact with stereo B some time ago. We got it back for a short time in September of last year, but then unfortunately we lost contact again. We're still trying to contact it right now. There's a possibility in May, and then after September, we're not going to try again until about 2020, assuming we don't make contact again. We won't try again until about 2020 when it's a lot closer to us, and so we have a better chance at it. Okay, and there are a couple other small issues mentioned, a reset and on stereo, and then, on Themis. and some hours that were lost, and a TDRS issue on MMS. But for the most part, these are all operating fine, we're getting data fine, and they're being highly utilized as well. Okay. Well, this clicker doesn't like to move the slides around. Okay, I'll use that. Okay, so ICON, or Ionospheric Connection Explorer. ICON was one of our Explorer class missions. It was primarily planned to study the neutral atmosphere and the ionosphere, so the thermosphere, the very upper layers of the atmosphere. And it is in a region that is particularly interesting. You could say that it's a cross between what terrestrial weather is, what is happening, and what's happening in space weather. So it's looking at forcing from above and forcing from below. So that's the science of it. And what I'm showing up here on the screen, you can see that it's finished a lot of testing, has quite a few recent accomplishments, and it's got its thermal vac testing done, comprehensive performance testing, various others. The EMI, EMC testing is complete, and the Pegasus is ready to go as far as their launch vehicle. Upcoming milestones, well, pre-ship review in July of this year, and launch readiness date in October. So just after our last mission that's in prime phase, MMS, goes out of prime phase, then we launch a new one. So we'll have ICON taking new observations. And just a picture here of it installed in Arizona, but that was a picture back in March. Okay, and then there's GOLD, which is a UV imager also of that same region, particularly the neutral atmosphere, the thermosphere, and maybe a little bit of the mesosphere. So in conjunction with ICON, this will be quite a pair, because GOLD can view from a distance and see and image the entire disk of the Earth, or of the atmosphere of the Earth, at the same time that ICON is doing in situ measurements. So it'll be a good combination that we're really looking forward to. Tom Emmel, who is the ICON PI, was visiting headquarters a couple weeks ago, and he's very worried, well, not very worried, a little bit worried and very excited, mostly excited. But these two together, as I said, are going to be quite a pair. GOLD is one of our missions of opportunity, which means that any mission of opportunity is something that launches on some other satellite rather than a NASA launch. And in this case, it's the SES-14 satellite. And the launch of that is supposed to be in 2018. I don't know the exact month of that. Sorry, I didn't get that fact in my arsenal before giving this presentation. Okay, Solar Probe Plus. Solar Probe Plus is going to go really close to the sun. I mean really close to the sun. At closest approach, 8.5 solar radii away. So it's really looking to understand and measure the outer corona and look at acceleration processes for the solar wind and also heating of the corona. So that mission has gone through a lot of testing. Also, as you can see up here, the solar array cooling system now is integrated. It's in thermal vac at Goddard. The thermal protection system qualification model is completed. It's acoustic testing. And so I won't go through all of those tests. You can read them as they're up there. But it is in good shape. It is passing through quite well. Of course, this is going to get really close, and there's a lot of layers of protection against the sun because it's going to get pretty hot. We don't know exactly what will happen, but based on our best knowledge and guesswork, maybe I shouldn't say guesswork, it's probably a little bit better than that. It will probably do quite a very good job. So upcoming milestones: pre-environmental review in September of this year, pre-ship review next March, and then its launch readiness date is July 31st, 2018. So we have quite a bit coming up on the horizon. Okay, Solar Probe Plus, then Solar Orbiter. Now this is an ESA mission, and we have 2 instruments. NASA has 2 instruments and also the launch for this mission. This is looking also at the heliosphere right around the sun. So this one is going to get closer into the sun than the orbit of Mercury. Not nearly as close as Solar Probe Plus, but still pretty close, and it's in an elliptical orbit. So it has a lot of accomplishments recently as far as now I'm just talking about the instruments in the NASA side, but we have shipped the heavy ion sensor to MSSL. The heliospheric imager team has closed all of its actions and with the pre-ship review, and that has been shipped to the Airbus in Stevenage, UK. So its launch readiness date, the milestone down at the bottom, is now February 2019. So those are our 4 missions in development. I have one slide that summarizes those 4 icons: Gold, Solar Probe Plus, Solar Orbiter, and these are pictures that I showed of basic hardware or parts of it, and I think I mentioned all of these tests. So this is a snapshot of where these missions are at the moment. Okay, sounding rockets. Now, you're probably all familiar with sounding rockets, but in case not, sounding rockets are suborbital missions. They just go up and they come back down. They take about 20 minutes to accomplish that. They are really useful to us, though, because of getting to an area that we can't get to very well with balloons or with satellites. So show up here 4 different locations from which we launch sounding rockets: Wallops Island, Poker Flat Rocket Range, White Sands Missile Range, Kwajalein, and this is in New Mexico, this is in Alaska. Wallops Island is just off Virginia. Kwajalein is in the Pacific. It's west of Hawaii and east of Singapore, a little bit northeast of Australia. There's also a possible 2019 campaign to Australia. So the missions that are shown here in the filled-in triangles, these are all ones that have launched. They have been quite successful. This range in particular from Poker Flats, they go up into the aurora, and they look at variability in the aurora. They look at the neutral winds that are up in that area. And that is an area that we can't reach any other way. So they provide very unique measurements so that we can have a better understanding of processes in the aurora. The other ones that are coming up soon in the end of April or May, these and this, they're all showing green. They're all ready to go. The Hassler rocket, all of that team is in place at White Sands, and they should be going, well, quite soon, early May. I don't know the exact date of that launch. Okay, so this shows the Black Brant rocket, sounding rocket, and a couple of pictures. This picture on the right is from one of the launches recently that went up into the aurora, just so you can get a good picture of what they look like when they go. And this Black Brant is the workhorse of the sounding rockets. It's been in development and use since the 70s. It's a Canadian rocket. We tend to purchase many of them at a time. You can put other stages on underneath them so that they can reach even higher in the atmosphere. But that has been a very successful sounding rocket for us. And one of the reasons for putting this pictures in here right now is that Steve Clark was up there recently. He saw one of these, well, he waited around. I don't think he actually got to see the rocket launch, but he was there for a while. When they're there, they usually stay until there's something really exciting going on in the aurora, and then they can launch into it. Okay, so I think he actually missed the launch, but it was close. Okay, so that is, I've shown you the operating missions, I've shown you the missions in development that are coming up for launch very soon. And in addition to that, we have put out some AOs. We have put out the Explorer AO, it was a SMEX, along with the Mission of Opportunity. That went out in sometime, I think it was in 2016, in fiscal 2016. The awards are expected this July. So we will know what, at least what phase A's are going to go forward at that point. In addition to that, we just released a draft AO for the IMAP mission. If you want to know more about the IMAP mission, there is a session on it tomorrow afternoon here. I don't know what room it's in, but you can check the program. That is coming up. We did not release the MOO for this at the same time. There will be a MOO, possibly two. That will be released probably in July, August, still of this year. As far as LWS program, we're going to have a science definition team established starting this year. And we're looking at the science definition team for STP 6 and 7. And that will be in fiscal 18. So we have quite a few in operation. We have some about to launch, and we have upcoming ones that the AOs are out there, no selections yet. Okay, interdisciplinary science. Planetary's Juno mission has been up for a while. In fact, I saw it in the New York Times on my way over here on this trip. It has just made some dips down. It's above the clouds and dips down in because it's looking at the turbulent atmosphere of Jupiter. And because a lot of what they're doing overlaps in Planetary, overlaps with Helios physics, we are looking at a possible participating scientist opportunity. We're talking about that right now. I can't give you a date on when it'll be out, but it is part of the picture. There are many different things that we could look at for this opportunity, including solar wind magnetosphere interactions, perhaps reconnection, comparative magnetospheres. We have done that before. Atmosphere, ionosphere, magnetosphere interactions. And so these are all possibilities, so stay tuned for this. This opportunity should be out hopefully sometime this calendar year. International partnerships. Okay, there was a recent NASA-ESA bilateral in Paris. This is an annual meeting that takes place, and at this particular meeting, I wasn't there, but Steve tells me they discuss things like missions in operation as well as upcoming possibilities and any possibility of a joint mission. And at this particular meeting, they were discussing along with JAXA a possible next generation solar mission. So the CASI group came to NASA headquarters just recently, a couple weeks ago. I was at that meeting. We were discussing possibilities of a coronagraph on a balloon flight, and we were also talking about, or they have a possible opportunity with CubeSats to launch CubeSats to study magnetosphere, ionosphere processes. JAXA, as I mentioned, we have a possibility with a joint with ESA to look at the next generation solar telescope. Let's see, there's a draft report, that's right, it's due in April. In fact, it's due this week. And the final is probably going to come out in July. For ISRO, there's been working group meetings held, not in person, but video teleconferencing. And there are 3 subgroups that are established with them. Aditya, one mission, that is a coronagraph, and I forgot the detail of what that was, besides being a coronagraph, but it's, I think, launching in 2020. That's right. I think the possibility of launch is 2020. They're also looking at space weather modeling, long-term strategic collaboration focus areas. So there's quite a bit going on between NASA and other agencies. Okay, communications and outreach. I'm running out of time, I think. So we used to do primarily press conferences, but that's old news now. We're much more likely to do social media these days. We have, if we have a story, a paper that goes into publication that we want to make a splash about, then we do a web feature story in addition to social media in terms of Facebook, Snapchat, Instagram. I didn't even know what Snapchat was until fairly recently, but these are ways to interact that we didn't have available just a few years ago. We also have, and you can see up here how many people are accessing our stories through these media. We have, for example, Snapchat, 1.6 million people. Tumblr has 1,700 shares. So we get lots of comments, we get lots of views. So this is a great opportunity and a new opportunity for us to broadcast important news about our field and what progress we have been making in heliophysics. Okay, just briefly, you probably all know there is a solar eclipse. This is very exciting in the US because it's been 26 years since we have had a solar eclipse, and that was in, I think, mainly in California, and then didn't cross the entire US like this one is going to do. I think it came down in this direction. So the last time that we had something like crossing this much of the US, I think we have to look back 100 years or even more for that opportunity. I'm planning to be right here because I have family in that area. So many of us in heliophysics are going to be populating that totality red line across the US so that we can bring the story of heliophysics to a very wide audience. We're engaging with those communities and establishing partnerships so that we can, different people pair up so that we can go and we can talk up our science in addition to seeing this fantastic event, which I've never seen before. I'm looking forward to it. Okay, and one last thing, which is that while Steve was up at the rocket range, he also went and gave a presentation at a school and sharing the story of heliophysics, but he also got to witness, there were a number of different tribes, including the Inuit, that he was able to go and to see one of their native dances and just pageantry during the time that he was up there. And then just, you can't have a picture of Alaska without showing some of the wildlife. And this was their attempt to make a palm tree. I don't know if that succeeds very well, but that's what they were trying to do. Forget about the snow, think about the warm. Okay, so I think that's it. Thank you very much.
I can use this one. Thank you, Mona, for this nice overview of heliophysics activities at NASA. So we have time for questions. Yes, please.
As solar physics and space weather is critical also to support human spaceflight missions. So are there specific experiments measuring space weather that you do in support of human spaceflight and operation or the Moon and Mars program?
You're asking about space weather measurements that we do. There are several satellites that contribute to space weather observations, particularly the ACE spacecraft that provides the upstream or incoming from the sun. The Van Allen belt, the Van Allen probes in the radiation belts provide up-to-date information about the state of the radiation belts. And those I think are the primary NASA assets. There are many other assets, plus our models, a lot of models that are developed and held at the CCMC, the Coordinated Community Modeling Center. Those are used very heavily in space weather. Does that answer?
You have also solar experiments on the International Space Station, and some of them are funded partly by human spaceflight programs. So are there more heliophysics experiments which are funded through this channel as well?
Are you asking, heliophysics experiments funded by the...
HOMD, the human exploration and operation.
We do have at least a CubeSat that went up to be launched from the space station. I don't know of any funding by that division that feeds into heliophysics. There's certainly cross-interest in it because naturally things that affect the astronauts are very important, and so there's certainly cross-communication between them, but I don't know that we've passed any funding back and forth.
We have time for another question. So, if not, thank you, Mona. So, next talk will be given by Luigi Colangeli from European Space Agency about the status of the ESA science program.
Okay, thank you. Good afternoon. So I'm Luigi Colangeli. I'm the head of the Science Coordination Office of the Science Program in ESA. And I will try to summarize in this presentation the status of the science program. So essentially my contribution will be divided in two parts. One is essentially about status of our program in terms of missions that are ongoing. I will not go into too many details about scientific results because in this conference there are plenty of presentations that cover results coming from our missions. And then I will touch base a bit on the future and the present plan for the future activity in the science program. So this is the typical picture that we show when we go to this kind of conferences that gives a sort of summary of our missions in the solar system. Of course, these missions cover both the solar physics, the solar terrestrial interaction, and planetary physics, because in our structure it's a single unit taking care of these activities. Many of these missions are led by ESA, others are led by international partners in which we collaborate, providing contributions, or the other way around. I would like to start with something from the past, that is a movie, a sequence of images taken by the Giotto mission in 1986. So this was one of the, well, it was the first time we got images of a comet nucleus, and this is the sequence that the Giotto mission was able to deliver to us. So quite a different scenario from what we know now about comets. And I like to report this because if we go to the next one, it was 1927 when the first document describing the Rosetta mission was produced. And in this picture there are two messages. It was 1987, that means several years ago, before we went to a comet and do really the Rosetta mission. Second, as you read down there under the title, it was at that time a comet nucleus mission, sample return mission. So it means that these challenging missions like Rosetta, first of all, require a lot of time. They require a lot of technology developments. They require a lot of preparation work. And they evolve in terms of what you can achieve really in reality with a mission like Rosetta with respect to what we originally as scientists wanted to do since the beginning. So we have to cope with this situation where we go to do challenging missions in the solar system and in general. So if we go to the next one, this is the present. So this is one of the beautiful results that the Rosetta mission was able to achieve thanks to staying with the comet for a long period. So we went, what I say, from the Giotto situation in which we had really a sequence of images towards something that is instead a full movie of the behavior of a comet nucleus through all the period going around the sun. So certainly this gives you quite an interesting picture about what we can do in studying small bodies, but at the same time it gives you a flavor of how difficult it is to do these kind of things for the benefit of the scientific community. I cannot avoid to mention that the Rosetta mission was one also of the cases in which we had a good collaboration with NASA. In fact, some of the instruments on board the Rosetta mission were produced under the leadership of a principal investigator from US. Next one. Well, this is another, let's say, for me, quite interesting picture. This is one of the images taken by the Rosetta orbiter towards the surface of the nucleus. And if you look at the red box there in the bigger picture and you zooming out, what you see here at the bottom is essentially the image of the lander. You remember that we finally were able to deliver a lander on the surface of the comet nucleus, and it took a bit of time before we discovered where it at the end ended up after jumping on the surface of the nucleus for some times. And again, this was one of the most interesting results of the Rosetta mission. We are talking something happening in 2014, and this comes 9 years after the landing of the Huygens element on the surface of Titan. It's important because we celebrate in these days, actually in September, another important mission like Cassini, with the end of the mission happening after the summer. Another beautiful example of collaboration in which NASA made a wonderful mission with Cassini, and in which ESA was able, with the Italian Space Agency, to provide a lander that finally landed on Titan. Next one, please. Well, to touch base on something that is more on the solar-terrestrial interactions, I don't want again to enter results of the cluster mission because there are sessions here where these are discussed and presented. Perhaps it's important to mention that cluster is still operative after about 17 years of activity. It was launched in 2000. And still, extension after extension, as we do technically in our mission procedures, still it's delivering excellent results and wonderful data with these 4 spacecraft flying together in a formation sometimes as close as a few kilometers one from the other. And we have still to come interesting new possibilities of doing new science with the collaboration with MMS, because in this case, in the period 2017-2018, we have the opportunity of having 2 groups of 4 spacecraft looking at the global picture of the interaction between the solar activity and the terrestrial environment from different positions with different instruments, and with instruments that nowadays on MMS, of course, are of the next generation with respect to cluster. If you can click on the black box. Yes, thank you. Well, this is, yes, just on the little arrow, yes. Yes, it's working. Thank you so much. So this is not typically a planetary mission. It's Gaia. Gaia is a mission that nowadays is operating nominally, and it is an observatory mission. And the keywords of this mission are astrometry, photometry, and spectroscopy. It builds up on the experience and the knowledge that we have developed with the previous Hipparcos mission, and nowadays is performing again a wonderful investigation of the sky in 3D. So essentially the purpose of this mission is to look at the sky and you see scanning the sky several times. So you really can not only characterize the position of each single object observed, but also to characterize the proper motion. So you really have the opportunity to describe the position and the evolution of our sky in 3 dimensions. And I wish to mention this because it's a typical example of an astronomy mission delivering also excellent results for planetary physics, because thanks to Gaia, we are now characterizing more and more also, for example, asteroids in the main belt part. That means that these kind of missions are really multi-purpose and are able to satisfy a wide range of interests and communities. Let me, for example, remember one number that is 7 micro arc second is the precision that we can achieve for an object of 10 magnitudes in the visible range. This picture gives you also a sort of chart of the results obtained and published in the first data release in 2016. We are now working towards the next data release that will come in some months from now. Next one, please. Okay, this is one of the wonderful pictures in which you see really the characterization of the sky thanks to Gaia. Next one, please. Well, this is another field in which ESA is very active, and this is about the preparation for future characterization of gravitational waves from space. What you see here is the core of what we call the LISA Pathfinder mission, and the core of this mission are 2 gold platinum cubes that are 46 millimeters in dimension, and they are caged in an environment in which the distance from the walls where they are captured is of the order of 4 millimeters. And this is a typical example of a mission in which we demonstrate technologies. It's in preparation, as I said, for a future gravitational wave mission, and the main purpose of this mission is to be able to demonstrate that we can really do interferometry with high accuracy in space to use drag-free motion and to analyze the micropropulsion behavior of the system that are on board. And if you go to the next picture, you see how the mission is behaving. The LISA Pathfinder is delivering this kind of profile in terms of noise due to different acting forces that are perfectly taken into account and some way compensated. And if you look at that higher curve there, that's the requirement that we need to have for the LISA mission. LISA is the future mission that we are in our plans now for the observation of gravitational waves from space. So essentially, LISA Pathfinder has already achieved, of course, on the scale of the LISA Pathfinder mission, the degree of low noise that we need to have the LISA mission performing. So really, LISA Pathfinder is not, of course, since it has a technology demonstration mission delivering scientific data, but is a clear element that we use in the future years to build the LISA mission, and I will touch base on this later on. Okay, so going towards the, let's say, near future, we have 2 big important events coming in 2018, let me say. One is the launch of the James Webb Space Telescope. This is, of course, a NASA-led jewel that they have in their program, but it's a mission in which ESA and the Canadian Space Agency are collaborating. In fact, we have instruments that are built from the European community on board the James Webb, and the launcher of James Webb will be provided by ESA. So it's a typical big example in which, and the message of this chart is exactly this one, in which if you want to have big results and big missions, we need to have large and important collaborations between large space agencies. And clearly James Webb is one of these cases, as well as Bepi Colombo. Bepi Colombo, just by chance to be launched now more or less at the same time of James Webb, is another mission in which we have the opportunity to collaborate with JAXA in this case. And in this movie you see the 2 spacecrafts. The one going around the planet closer is the one that will be observing the surface and the characteristics of the planet, while the magnetospheric orbiter built essentially by JAXA will examine the magnetospheric environment and the environment in general of the planet. The image on the right side comes from the Messenger mission, and I put it there because I think nowadays with the results that Messengers has delivered to us, certainly Bepi Colombo, in my opinion, assumes even a more relevant role for the future because there are characteristics of these two spacecrafts with their configuration and their distance from the planet, and the instruments on board the missions will be able to really disclose new elements and new considerations about the behavior of Mercury. I think you have jumped one. Next one. Okay, perhaps it has gone. Anyway, this is an image that should show how the mission called SMILE is expected to behave. SMILE is a mission in which we have a collaboration with another partner, is China in this case. And this mission has been selected in collaboration with the China Academy of Science. So it's the first time in which ESA collaborates with China to perform really the complete process of selection and implementation of a mission together. It's a mission that will explore the interaction between solar energetic events and magnetosphere. And what you see, if we can run again the movie, here is a sort of simulation about what would be observed. Essentially, the two spots that you see there are the polar cusps where the solar wind enters the magnetosphere, while the edge on the right side is essentially the shocked region determined by the solar storm. So with this mission that includes in particular an X-ray telescope, we will be able to characterize this kind of phenomena through this new and collaborative mission with China. Next one, please. Okay, so this is a sort of picture and framework on where we are in terms of missions that are running or that will be soon be launched. But let me say more in general that the approach that we have in our science program is driven by two elements. First of all, we look for the science excellence. It means that we need to have a very competitive process in selecting our missions, and in fact, all our calls are based on peer review analysis of the proposals that are submitted through our calls. And the other important point in the science program is that it is a mandatory part of the program. It means that every single member state member of ESA is expected as to contribute to the funding of the mandatory program through a proportional element that is related to the GNP, the national GNP. This means that we have a sort of stability in our funding profile for the coming years, and therefore we can envisage what is the profile of opportunities that we can offer to the community for missions to be included in the science program. And as I said, this is a bottom-up approach in which essentially we have a science advisory mechanism with bodies that are in the different areas of our science, solar system, astronomy, and physical science working group. And these groups include essentially members of the community. Then we have an higher level advisory committee, again formed by scientists. And this pool of scientists have the role to recommend and to advise the director, the executive of ESA in science, towards the decision to be taken on the missions to be selected. But the important point is that the decisions are taken by the Science Program Committee. This is the only body really in charge of having decision taken about missions selected. And there is where the different member states sit with one representative each. So it's a bottom-up approach, but at a certain point is a, let's say, programmatic decision that comes from the member states. And by this approach, we have some elements that are part of our program. There are what we call the large missions. Essentially, these are missions that we consider the flagship of our program. And what you see here in the pictures are some examples from the recent past or the present. Essentially, they absorb about 2 annual budgets in our budget. Consider that our budget, yearly budget, is of the order of 500 million euros. And clearly this implies some effort in terms of innovation and technology development, and they must guarantee a sort of leadership in the scientific fields where these missions are launched. And of course, due to these budgetary elements, we plan usually to have one of these missions every 7-8 years. Then we have the next one, please. We have the more flexible part of the program, that are the medium-class missions. And these are missions in which essentially we could also consider spending this quantity of money that is about 1 year, annual budget year, for a collaboration, for a contribution to a mission led by another international partner. And clearly it's still hoping to obtain excellent scientific results, but the time of development should be shorter, and therefore the technology that we intend to use for the mission should be much advanced, much more advanced than what you can expect for a large mission. And finally, we have other elements in the program, like the small missions. This is a new concept that we have in our program, and in fact we have Cheops, that is an exoplanetary mission that I will mention later, that is a part of the program, and missions of opportunity. Missions of opportunity are cases in which we contribute at a small amount, of the order of some tens of millions, to missions led by other international partners. And this is the only element in which we don't have a competition, because, of course, if there are opportunities, they have to some way be available on a fast track, but at the same time, the Science Program Committee always has to vote and eventually approve these kind of contributions. Okay, this is a chart in which you see essentially the past, the present, and the future of the different missions that are in our program. The green ones are in operation. Many of them, as I said before, have been living for much longer than originally planned, but they still are operatively in good shape, and they deliver science, good science, so we keep them operative. Some of these missions have already passed their operation phase and are in post-operation. Others are under development and they will come to operate soon in the future. Let me mention that one mission that is not reported here, because also the post-operation phase of it has been concluded, is mission Smart 1. And I'm glad to report that perhaps on Wednesday morning and Thursday morning there will be some new release of interesting images of the surface of the moon, and perhaps these images will release some information about where Smart 1 at the end ended up at the end of its life. In fact, Smart 1 was delivered to the surface of the moon at the end of its operation phase. So please go and listen our former project scientist Bernard Fuang about the results that will be shown during these sections. Okay, this is a sort of picture that shows where we are in terms of future missions. And again, you see the three classes of missions. JUICE is the next large mission in the solar system. I have a chart about it. Athena is the second large mission in our program, that is an X-ray observatory mission. And the third one is what we call now LISA. Formerly, it's still a gravitational wave observatory mission, because the mission name has not been assigned and the mission team has not been appointed, but we are in the process to complete this process. So very soon we will have a name also for this gravitational wave mission. The three medium-class missions that we have on our path are the medium number 1 solar orbiter. Second one is Euclid. It's about dark energy and dark matter observations. And Plato, that is a mission exploring essentially exoplanets through looking at the transition of the light curves. Small missions, Cheops is again a mission dedicated to study exoplanets, and this is a mission in which we have a strong collaboration between ESA and member states, in particular a consortium led by Switzerland and other member states having a relevant role in this mission, and SMILE, the mission I mentioned before, in collaboration with China. So you see we have a variety of opportunities and a variety of missions that are already on the path to be implemented. Actually, they are most of them already in the implementation phase. Next one, please. Well, one chart or two actually perhaps on Solar Orbiter. It was mentioned already and by the previous speaker that this is a wonderful collaboration between ESA and NASA. NASA is providing instruments and it will provide, they will provide also the launcher. Essentially, it's a mission that will study the sun, but it will have two main characteristics. It will go very close to the sun at the level of 0.3 AU, and it will work for some of the phase of the operations at very high inclination. So this will allow really to have a different view of the sun, of our star. And the other important feature is that on board these missions we have both remote instruments and in situ instruments. So we will be able really to analyze the behavior of the machine called sun through these two different approaches. If we go to the next one, there are some indications of what I already said. The present launch date is February 2019. And again, we hope to go to a distance of 0.28 AU as closest approach and to an inclination of the order of 33 degrees during part of the mission. Next one. Okay, this is the ESA China mission I mentioned before. Now it comes the view graph I was expected to have before, but essentially these are already reported. This is a mission that will study the solar wind magnetosphere ionosphere interactions, and it will be a collaboration with China. Next one, please. Yeah, the last one I want to mention is, of course, JUICE. Many of you know that JUICE is our future large mission in the study of the solar system planetary mission. And the next chart will tell you where we are at the present time. It's a mission that will not only study Jupiter, but will also study the two moons, Europa and Ganymede. Actually, we will enter in orbit around Ganymede, and we will have a long period of order of 1 year looking at the characteristics of this moon. And we are quite on track at the present time during the implementation phase of this mission. We expect to have the readiness of the spacecraft for instrument integration in 2019. So far, the activities are running as expected. So for the time being, we are able to maintain the June 2022 as launch date for this mission. Okay, the last 3-4 minutes I want to spend is about really the really recent past and the future. That means we, as I said before, have to cope with the financial situation and with the availability of funds for the implementation of these missions and of our program. And so what happened, and as it happens every 3 years, we had last December 2016 what we call the Council, the ESA Council at ministerial level. So essentially all the ministers of the member states sit together and decide the funding for the coming 3-5 years. As I said, the science program has the possibility to count on what we call a mandatory support for the activities, but at the same time the Council has to establish the level of resources for this kind of activities. And what it happened already in the previous council, and it happens again, is that we didn't get, in reality, inflation compensation. So this means that for the coming 3 years at least, or 5 years, we will have to adapt the science program to the availability of resources based on the assumptions about the inflations that will, at the end of the day, will reduce the purchasing power of the program. And in fact, we have discussed this, if you can go back to the previous one, please. Yes, we have discussed recently with our stakeholders, in particular the SPC members, the member states, what are the lines that we have to follow. And this has been discussed in a workshop early of April. And at the end, in June, at the next SPC formal meeting, we will present to them what we have understood from their indications on what to do in order to make, again, our program compatible with the resources available. Some sacrifice is required. There is a clear indication that we don't have to sacrifice the large missions, because these are certainly the pillars of our program. Probably we will have to sacrifice something in the medium-sized missions. And this is why recently we some way slowed down the process of the selection processes that we are running for the M4 and M5. So based on this, we are now ready to go in front of the advisory structure and then in front of the SPC in May, June for the formal adoption. Is a formal step that we have in our program after a study phase of the candidate missions for them 3 mission plateau. So if everything goes well with this adoption process, formally the implementation phase of the plateau mission will start after June. And then, next one please, we have to deal with the 3 candidates that have been studied in the past 2 years for the M4 opportunity. There are 3 candidates in competition nowadays, Ariel, Tor, and XIPE, and you see here what kind of missions we are talking about. As I said before, we have done all the technical and programmatic study of these candidates. Now we have to start the scientific evaluation. Next one, please. And in fact, it's a very, complex chart. I don't want to explain all the details, but essentially the dashed line explains where we are now. We have completed the study phase, so we have to enter now what we call the science assessment phase, where a science assessment review panel formed by independent scientists will analyze the 3 candidates, and after that a senior science committee essentially will recommend, according to the process that I mentioned before, to our director which of the 3 missions should be selected for M4 opportunity. Again, we slowed down the process. Now we are restarting this process with the hope to complete this one by the autumn this year at the latest. And then, to conclude something different, it's about new ideas. We ran last September a call for new science ideas in the science program. So this was not a call for real missions. It was a sort of way to stimulate the community to come up with new ideas that are not mature at all, so not ready to be competitive with respect to the usual process of mission selection. And indeed, we received some interesting proposals in this respect. There was no a priori technical screening because, of course, the ideas in principle that we had received had to be not mature. And there was, again, through the advisory structure, an evaluation of these proposals, and we came out with 3 themes on which now we will try to do something to improve the readiness of these fields. The first one, next chart, is about quantum physics. In fact, this was one of the fields in which we received a number of proposals. And so, essentially, what we will do now is to put this community together in a dedicated workshop, try to identify the technical requirements coming from the scientific objectives that they have in mind, and run what we call a CDF, a concurrent design facility study, to see to which extent a sort of mission related to this subject can be, could become feasible. Of course, this study could bring to the definition of some technical areas in which development is needed, and so new results will be needed through technology development. But at least we will have at the end of this process the opportunity to report to the community something that they can use for the future for new calls. The next one is about planetary science. In this case, there is a focus on planetary missions based on small platforms. We will follow more or less the same approach. We are planning to organize a small workshop in which the teams that were proposing ideas in this field and perhaps other representatives of the community will be called to discuss about the common elements that are needed in this field. And then we will run a study to see to which extent and to which level of scientific objectives a small platform can be prepared to serve this community. And finally, the third theme is about high accuracy astrometry in the near infrared. This is something perhaps a bit more specific because there is a lot, as I said before, coming out from Gaia, and one of the ways to improve and to continue in the same area is the possibility to use infrared wavelengths to explore the galaxy. Again, also here we will have a study to understand to which extent we can proceed in the infrared with the new mission concept. So as you see, we are trying to explore on one side the missions that are more or less mature to become elements in our program. On the other side, we are trying to also stimulate the communities and eventually communities that have not had access to the space environment so far to come in our system and work with us, discuss with us these opportunities. I think this is the last chart in my presentation, so I'm ready to take your questions if you have any. Thank you.
So we can go directly to questions. Yes, please.
I would like to ask about the M5 mission proposals. So we understand that there is some slowdown of the process following the ministerial conference. However, for the mission proposals that have been already submitted, is there some preliminary schedule on when the scientific assessment of these proposals will be done?
Yes, thank you for the question. In fact, it was one of the points I wanted to mention as a part of this, so to say, re-planning of the activities for the science program. As I said, there has been a delay in all these activities because we wanted to reflect about the outcome of the ministerial conference. So now the first step is to go for the adoption of Plato in the next SPC, if it goes through. And then to complete the M4 evaluation, as I said, by autumn time frame. And by that time, we plan to restart the evaluation process for the M5 proposals.
Thank you.
Yes, Tinman.
Luigi, the obvious question, what is a small platform?
That's exactly what we would like to discuss with the community, and it is something that came up clearly in some of these new ideas. You know, as a planetary scientist, let me say, I've always the problem that when we go to look at proposals coming in our M-class missions, usually they are, let's say, hitting the top budget availability in terms of what you can do. And very often these missions are refused because they are too expensive or too challenging from the technology point of view. So the idea that we would like to explore with the scientific community this time is exactly that one, to see to which extent we can build a small platform that is compatible with, for example, to give an example, a Vega launcher or something like that, that can accommodate certainly not the same science objectives of a mission like a large medium class mission, but something more focused and more capable to be flexible from this point of view. So the exercise we want to do with you is exactly to understand if there is a potential from a mission like this to satisfy a targeted scientific objective, and if this kind of characteristics of a platform can be then offered to the community to come with proposals sized properly to this kind of platforms.
Okay, thank you.
Thank you. I think we are running out of time. Thank you again, Luigi.
Thank you. Sorry for that.
Okay, good afternoon. Thank you very much for staying that late with us for the last presentation. So the story of this study is an idea from the Air and Space Academy in Toulouse, which was implemented with the EC in Bern and with Europlanet. And the idea really is to try to do some foresight about the major questions which are going to drive planetary exploration to the horizon 2061. So 2061 is a really symbolic date. It's the date of the return of Comet Halley in the inner solar system, so it's the next opportunity for going to Halley. And it is also the first centennial of the first human space flight. So it's a double anniversary, I would say. So the idea that we are pursuing here is to try to see what are the big questions we have about the solar system and what are the space missions we would like to fly to address these questions. And we want to do it with the perspective of placing the science of the solar system in the broader context of the science of planetary systems as well, at the time of a very expanding, quickly expanding exoplanet science. So, does it work? Can do it here? No. Oh, yes. I click. Okay. So the first idea we would like to stress is we want to produce 50 years or so foresight of planetary exploration, and we want to base it on what we call 4 cornerstones. memorize something else, but the four cornerstones of planetary exploration, as we see them, are what are the major scientific questions? Second, what are the representative planetary missions we would like to fly to address these questions? Then, in order to fly those missions, what are the enabling technologies we need to make available? And finally, what are the supporting infrastructure we need to fly those missions? So we will not address these four pillars at the same time. And in the first exercise that was organized at Bern by ESA, where is it again? Sorry. Here? No. Oh, okay. What we did is to gather a forum, as he calls it, so a group of about 30 people with 6 conveners, with planetary scientists, and with about 10 space mission technology experts that helped us actually to address not only the science, but also the technology of those missions. So, again, where? So you will have the possibility to have access to the results of this forum in terms of the different presentations by going to the web page of ESA, the International Space Science Institute. You have the address here, and you can go through the tree of the web page down to the place where you can have access to the individual presentations that were made during this workshop. So let me show you now essentially how we go about the conclusions of this workshop. First, what we want to do is really to think about not just the solar system, as I show here, but also about the different classes of planetary systems. The second class of planetary system is the giant planet systems, and we think they play a very important role in this perspective, because that is the place where inside the solar system you can sort of address the science of a planetary system as a whole. But naturally, another place where you could and should address the science of planetary systems is by looking at exoplanet systems, and there are many now, as you know, several hundreds. So what we did essentially is to think about the types of questions we have about the whole class, and then, as a second step, at how we could address part of these questions by looking at the solar system. So the first thing we need to say is that planetary systems are characterized by the set of objects, and those objects display a variety of coupling processes. I am presenting here 2 basic coupling processes which you know very well: gravitational coupling and electromagnetic coupling. Gravitational coupling governs more or less the dynamics of the solid bodies, let's say, and the tidal interactions, the evolution of orbits, and so on. But at the same time, electromagnetic coupling governs the dynamics of the plasma envelopes and how it connects to the central star. So we want to be able to understand how a planetary system works from these 2 perspectives, and probably from even more perspectives of different coupling processes. So that's the basic idea. Then, if those systems are governed by coupling processes, they are evolving with time, and we want to place our approach of scientific questions in the perspective of an evolutionary path for the planetary systems. And here you have a very simple cartoon of how we could go about it. Planetary systems on A essentially is formed, then it evolves, it forms planets, and then the planets become standalone objects, and in the end you have the type of system you can contemplate now in the solar system. So from formation through the contemporary objects, the key questions we think that should order this exercise is the question of habitability. Where are the habitable objects, and how do they happen to evolve and to be emerging in a planetary system? And that takes us to the question of life. Where can we find life in a planetary system? And to the, I would say, overarching questions which I have placed here. Are planetary systems life-generating machines? that would be the organizing questions we would like to propose for the study of planetary systems. And as you can see, it connects us to a very old question, this one: are we alone in the universe? So we are organizing the way we are studying a planetary system through this set of questions which are ordered towards the search for life. So it's a sort of arbitrary, but that's the way we have organized our search. So actually the solar system, as we know it after about 50 years of planetary exploration, is an ideal habitability laboratory. We know rather well now where are the habitable objects, and basically we know that there are two types of habitats. Surface habitats, essentially the Earth and marginally Mars and Venus, and we have to look into the terrestrial planets to understand better how habitability works there. And the other type of habitat that was explored and discovered, I would say, through the exploration of giant planets now is the ocean moons. So at Jupiter, Europa and Ganymede, and at Saturn, essentially Titan and Enceladus. And we know that at those places, there is liquid water, there is a stable environment to some extent, there are the essential elements for life, and there is energy. And therefore, we know we have a sort of templates for habitable worlds in the solar system, which is very important to explore. And also, they are a good place from which we could extrapolate the search for life at exoplanetary systems. So that's the whole logics of what we are trying to do. So now how to build a space program, or not a space program, but a set of space missions from this perspective. So the idea is that Horizon 2061, as we build it from this Bern meeting, would be a sort of, not a single mission, but a set of missions, or we might call it an integrated mission to the solar system. And let's build it in the same way that we build proposals for new planetary missions. I think we know rather well the mechanisms for that. We define what is the overarching goal, what are the cross-cutting science questions we want to address, then what are the key measurements objectives we want to define to answer the questions, then what are the space mission types and requirements, and finally, that's the last issue, what are the technologies and infrastructures that we need to fly those missions. So that's the logics of what we are planning to do. And in Bern, we started with only the science and mission parts of this development. So overarching goal, I am proposing one here, and for sure it is for discussion. It would be the study of the formation and evolution processes leading to the growth of complexity and ultimately to the possible emergence of life through the diversity of planetary systems. And it has two sub-questions. One is study the growth of molecular complexity from the interstellar medium to planetary and moon's environment. And two, study the growth of complexity of planetary environments and of the conditions under which their evolutionary path may lead them to become habitable. So in a way, the story we want to tell is the story of the encounter between the potential habitat and potential inhabitants, to make it simple. So from that, we can develop the questions that we want to address in this process of looking for the way habitability emerges in a planetary system. We have tentatively proposed 6 questions now, which are again open for discussion. First one, very evident, what are the initial conditions of planetary system formation? The second one, what is the origin of the diversity of planetary systems architectures? That's something we cannot answer only with looking at the solar system, clearly, because the solar system is not, in fact, particularly representative of the family of planetary system architectures. But this question of the diversity of architectures is a key element, we think. Then what is the origin of the diversity of the objects? And we know there is a full spectrum of planets that we have observed now around other stars. They include the planet types we know in the solar system, like gas giants, ice giants, terrestrial planets, and the small bodies and debris disk objects, and so on. And by looking at the solar system, we have a partial answer to the question of this diversity. Then the question 4 is, what are the coupling mechanisms? I think it was addressed before. 5, what are the conditions for the emergence of potential habitats? And finally, what are the strategies for the detection of life? Tell me if I'm beyond the time. No?
Yeah, you are perfectly on time.
Okay. So, in the context of exoplanet science, what we know essentially is that while we go towards 2061, exoplanet science will make progress in characterization of the exoplanets along this line of sort of the ongoing complexity, measuring orbits, mass, radius, mean densities, having access to the temperatures, albedos, atmospheric compositions through transit spectroscopy, partly to atmospheric dynamics, and maybe some point magnetic field, and very far distant in the future, I think, having access to some elements of the biosphere. So that's the story about exoplanets, but we know that in the solar system, we can do something very specific, much more specific, by going to the objects and performing specific key measurements. So I'm not sure I will go through the details of what we have put under the 6 questions here. So we have 2 slides with the 6 questions I presented before. And for each of the 6 questions, we have identified the key measurements that we should perform in the solar system to address the questions. So probably I'll let you answer, or maybe you take question B. What is the origin of the diversity of planetary system architectures? So we need to measure actually the elemental and isotopic composition, primitive bodies and atmosphere, and so on. The diversity of objects at the bottom of this slide, we need to have access to the internal structure and bulk composition, gas, liquid, solids of all families of objects, gas giants, ice giants, terrestrial planets, satellites, and so on, to make a full inventory of the reservoirs of primitive objects from which these planets have been built. And in the end, I think one of the key objectives is to establish what is the connection between the planets and the building blocks from which they were built. So I will go maybe beyond that and to the final slide. To go from the scientific questions and the key measurements to mission requirements, we need to sort of characterize what are the type of missions we need to use. And so we have identified mission types, mission targets, and space-time characteristics as a way of describing the mission types we want to consider in this study. So mission types, well, from far from the object towards very close to the object, the hierarchy is well, we start with Earth-based observations, then we do flybys, then we do orbital characterization of an object, then we establish the surface station, and we do some mobility at the surface, and finally the last step is to perform a sample return. What are the targets? Well, the targets for these missions are heliosphere and its interactions, planets or small body, a giant planet system or a moon. And what are the space-time characteristics of these missions? Well, it can be a single point, it can be a multi-point, and for magnetospheres, that's something which is very important. And in the near future, we will need to do multi-point measurements at outer planets, for instance, like we do at Earth, deploying a network or other possibilities. So from that, we are right now sort of building the traceability matrix of our set of missions. So you see the overarching goal at the left, the science questions, the 6 science questions, and you are just now filling the key measurements and the mission types. And the next step will be to identify the technologies and the infrastructures, and for that we will need another workshop on which we are working now and to which I would like to invite all of you to contribute. And this workshop about technologies and infrastructure for planetary exploration will be held at the Swiss Tech Convention Center in Lausanne, at the École Polytechnique Fédérale de Lausanne in Switzerland. The dates are set already, January 29th to 31st, and I hope many of you will contribute. Thank you very much.
Thank you, Michel. Yeah, we can start with the questions directly. Yanis.
Michel, on the mission types, did you also consider a 7th category, which is the subsurface access, particularly for the ice, considering going below the icy surface?
I should, yes, I will add it. Thank you, Yanis.
Yes.
Actually, yes, it's an interesting question because we had a discussion about that at the forum in Bern. And we thought, well, we are focusing on planetary science, not the interstellar medium. But we had the idea that we should identify actually a mission to Proxima Centauri planets in some time in the future. So it's a long-term perspective, but it's a good example of something that we will be able to accomplish only if there is a real revolution in the technology of propulsion. But I'm sure in the distant future it will happen.
I would like to advertise that every year the Space Science Department or S-Lab is organizing a large symposium, and the topic of this year is on extreme habitable worlds, where we are going to look at habitability on Earth, in artificial space, in the inner solar system, outer solar system, exoplanets, in the galaxy. And we are planning also to look at the technology, and in particular we look also at travel to the nearest solar system. You know, there are some projects like Starshot now that are looking to send some micro or nano satellite towards the solar system. So it will be interesting eventually to do also some prior brainstorming, maybe on the science side of some of this question before we go to the Swiss Tech event.
Sure. Yes. Yes. Yeah. Absolutely. When is it, Bernard?
So that will be the first week of December in ESTEC.
Oh, okay.
So it should be as cold as in Lausanne in January, I suppose.
Yes.
Yes.
So you're not integrating human exploration in these concepts or mission targets, doing in situ research on the planetary bodies directly, or?
Well, we did not start on considering human exploration, but we think that when we go for the second step, which is this technology foresight, we will consider human spaceflight actually as one of the entries to the development of the new technologies. And I mean, if part of the exploration is human, I mean, there is no question about that. I mean, at the Horizon 2061, I'm sure there will be a good fraction of nearby objects that will be again visited by humans. So it will be part of the second step, and the technology of it will be considered as one of the entries to our technology foresight exercise.
Thank you.
Okay, I think I'll thank you again, Michel, for this talk. And I thank you all for staying that late. And finally, I would like to get applause for all the speakers of this afternoon. Thank you very much.